Mars is a huge planet full of incredible mysteries that we are still discovering. This red world is millions of kilometers away from here and has gigantic mountains, valleys, and deserts. But there is one thing on Mars that changes everything we know about mountains. There is a mountain there so big that it makes Mount Everest look tiny. Olympus Mons on Mars is 25 kilometers tall, 3 times higher than the tallest mountain on Earth. This mountain is an ancient volcano, so wide that if you were standing at its base, you would not even be able to see the top because of the curve of the planet. How did a mountain so absurdly gigantic manage to grow so much? Why does Mars have volcanoes bigger than anything that exists here? Get ready to fall asleep while listening to this video and discover the secrets of this incredible place. Subscribe to the channel. Leave your like and comment from what part of the world you are watching. Get comfortable and relax. Let's begin. Imagine standing at the foot of a mountain so enormous that you cannot see its summit. A volcano so vast that entire countries could fit inside its base. This is Olympus Mons, the crown jewel of Martian geology. When humans first glimpsed this colossal feature through early spacecraft missions, it forever changed our understanding of what planetary geology could achieve. Olympus Mons formed through a remarkably different process than mountains on Earth. On our home planet, the tallest peaks typically form when tectonic plates collide, pushing the crust upward over millions of years. Mars, however, tells a different geological story. The red planet lacks active plate tectonics, which proved crucial in allowing Olympus Mons to grow to its extraordinary size. Without moving crustal plates, a volcanic hotspot in the Martian mantle remained fixed in the same location for billions of years, continuously erupting and depositing layer upon layer of lava in the same spot. This geological stability allowed molten material to build up gradually over an immense period, creating the largest volcano we've ever discovered in our solar system. The process began roughly 3 billion years ago, with the most significant construction occurring during Mars' Amazonian period. During this time, highly fluid basaltic lava flowed from the volcanic vent, spreading out across vast distances before cooling and solidifying. These eruptions weren't explosive like many on Earth. Instead, they produced fast-moving, runny lava that could travel enormous distances before hardening. Mars' reduced gravity played a significant role in the formation of Olympus Mons as well. The gravitational pull on Mars is approximately 1/3 that of Earth, which means that volcanic structures can grow much taller before succumbing to their own weight. This reduced gravity allowed the volcano to reach heights that would be structurally impossible on our planet. Scientists studying the lava flows on Olympus Mons have identified hundreds of individual layers, each representing a separate eruption event. These layers tell the story of the volcano's history, with varying thicknesses and compositions suggesting changes in eruption intensity and lava chemistry over time. The oldest layers, now buried deep within the mountain, contain the first chapters of the volcano's story, while the visible surface flows represent more recent activity. One fascinating aspect of Olympus Mons' formation is its unusually long eruptive lifetime. While most volcanoes on Earth remain active for perhaps a few million years, evidence suggests that Olympus Mons may have experienced eruptions spanning billions of years. The most recent lava flows might be astonishingly young in geological terms, perhaps just 2 million years old. This raises the intriguing possibility that the volcano might not be fully extinct but rather dormant, with magma potentially still present deep beneath its surface. The summit of Olympus Mons features a complex caldera system, essentially a series of overlapping volcanic craters formed when the magma chamber below emptied during eruptions, causing the surface to collapse. This caldera complex spans approximately 80 kilometers in width and contains at least 6 distinct collapsed areas, each representing a major eruptive event. The presence of multiple calderas indicates that the volcano experienced several cycles of filling and emptying its magma chamber throughout its history, as the lava flows extended outward from the central vent. They formed what geologists call a shield volcano, named for its resemblance to a warrior's shield lying on the ground. Shield volcanoes are characterized by their broad, gently sloping sides formed by highly fluid lava flows. The Hawaiian Islands on Earth formed through similar processes, though on a much smaller scale. The flanks of Olympus Mons also display fascinating geological features called lava tubes, natural tunnels formed when the outer surface of a lava flow cools and hardens while the hotter lava inside continues to flow. When the eruption ends, the lava drains out, leaving behind a hollow tube. On Mars, these tubes can be enormous, potentially offering future explorers natural shelters protected from radiation and extreme temperature variations. Around the base of Olympus Mons lies an impressive cliff known as a basal escarpment, which in some places reaches heights of 6 kilometers. Scientists debate its formation, with some suggesting it resulted from massive landslides, while others propose it formed through faulting or interaction with ancient Martian oceans. These cliffs provide valuable cross-sections of the volcano's structure, allowing geologists to study its internal composition. The weight of Olympus Mons is so immense that it has actually caused the Martian crust to bend downward beneath it, creating what's called an isostatic depression. This depression is masked by the height of the volcano itself, but sophisticated gravity measurements from orbiting spacecraft have confirmed its existence, unlike volcanoes on Earth, where erosion constantly wears away at the landscape. Olympus Mons has experienced minimal erosion throughout its long history. Mars lacks liquid water and has a thin atmosphere with weak winds, meaning that once formed, geological features can remain largely unchanged for billions of years. This preservation allows us to see the volcano in nearly the same state as when it was actively forming. The volcanic activity that built Olympus Mons also played a crucial role in Martian climate history. Gases released during eruptions, including water vapor and carbon dioxide, contributed to the planet's early atmosphere. Understanding the timing and volume of these volcanic emissions helps scientists reconstruct Mars's past climate conditions and why the planet transformed from a potentially warmer, wetter world to the cold desert we observe today. Studying the geological formation of Olympus Mons continues to provide invaluable insights into volcanic processes, planetary evolution, and the fundamental differences between Earth and Mars. As our technology improves and future missions deliver more detailed data, our understanding of this Martian wonder will only deepen, revealing more secrets about the geological forces that shaped our planetary neighbour. Number sign, comparative dimensions: Olympus Mons versus Earth mountains. When you think about the tallest mountain on Earth, Mount Everest likely comes to mind. Standing at approximately 8,848 meters above sea level. It's an imposing feature that has challenged climbers for generations. Now imagine a mountain 3 times that height, a volcanic colossus so large that if placed in the United States, it would cover the entire state of Arizona. This is the reality of Olympus Mons, Mars's geological giant that dwarfs anything we have on Earth. The sheer scale of Olympus Mons defies our Earth-based intuitions about what mountains can be, rising 25 kilometers above the surrounding plains. It stands about 3 times taller than Mount Everest measured from sea level. If we measure Mauna Kea in Hawaii from its underwater base to its summit, often considered Earth's tallest mountain using this measurement method, Olympus Mons still towers over it at more than twice its height. What's perhaps most staggering about Olympus Mons isn't just its height, but its footprint. The base of this Martian volcano spans approximately 600 kilometers in diameter. To put that in perspective, that's roughly the size of France. If somehow transported to Earth and placed in the United States, It would stretch from New York City to Washington, D.C. and west beyond Pittsburgh, a single mountain covering multiple states. The entire Hawaiian island chain, Earth's largest volcanic structure, could fit comfortably within just a portion of Olympus Mons. But volume calculations further emphasize the mountain's enormity. Scientists estimate that Olympus Mons contains about 100 times more material than Earth's largest volcano, Mauna Loa in Hawaii. The total volume of Olympus Mons approaches around 4 million cubic kilometers of material, enough to fill the Mediterranean Sea, despite its towering height. Olympus Mons would be surprisingly approachable for human explorers. Unlike the steep slopes of many Earth mountains, the flanks of Olympus Mons rise at an average gradient of only 5 degrees. This gentle incline means that if you were walking up the side of the volcano, you might not even realize you were ascending a mountain at all. The slope is so gradual that the horizon would simply appear tilted. You could theoretically walk from the base to the summit without any climbing equipment, though the journey would span hundreds of kilometers. The summit caldera complex, the collapsed crater at the top of the volcano, is another feature that demonstrates the mountain's incredible scale. This network of overlapping depressions spans about 80 kilometers across and drops up to 3 kilometers deep in some places. For comparison, the famous Ngorongoro crater in Tanzania, one of Earth's largest intact volcanic calderas, is only about 20 kilometers wide. You could fit 4 of these renowned Earth features inside the caldera of Olympus Mons. The surrounding cliff feature, or escarpment, that rings parts of Olympus Mons presents a stark contrast to the gentle slopes of the mountain itself. These cliffs can reach up to 6 kilometers in height, taller than the walls of the Grand Canyon. Standing at the base of these cliffs would be like looking up at a sheer wall twice the height of Mount Whitney, the tallest mountain in the contiguous United States. Earth's mountains formed through fundamentally different processes than Olympus Mons. Our tallest peaks, including the Himalayas, the Alps, and the Andes, primarily resulted from tectonic plate collisions when one plate pushes beneath another, forcing the crust to buckle upward. These processes are ongoing, with mountains like the Himalayas still growing a few millimeters each year. In contrast, Olympus Mons formed through countless volcanic eruptions at a stationary hotspot, allowed to build up over billions of years without being moved by tectonic activity or substantially eroded by wind and water. The atmospheric conditions at various heights on these mountains also reveal fascinating differences. At the summit of Mount Everest, the air pressure is about 1/3 that at sea level, making oxygen scarce and survival difficult without supplemental oxygen. The summit of Olympus Mons experiences even more extreme conditions. The already thin Martian atmosphere is only about 10% as dense at the peak as it is at the base. The temperature difference from base to summit is also more extreme than on Earth mountains, potentially varying by 70 degrees Celsius or more. The question of how long it would take to climb these mountains provides another interesting comparison. Everest expeditions typically take about 2 months, including acclimatization time. A theoretical journey to the summit of Olympus Mons, given its gentle slope but enormous size, would likely take several months of continuous travel, even with advanced vehicles. The distance is simply too vast for a quick ascent. Weather conditions present dramatically different challenges on Earth mountains versus Olympus Mons. Earth climbers face snowstorms, hurricane-force winds, and avalanches. On Olympus Mons, the primary weather concern would be dust storms, which can occasionally engulf the entire planet. The thin atmosphere means winds exert less force on objects, but dust particles can remain suspended longer and cause serious visibility and equipment problems. The geological age difference between these mountains is equally striking. The Himalayas began forming about 50 million years ago and are considered relatively young in geological terms. Olympus Mons, however, has been building for approximately 3 billion years, making it roughly 60 times older than Earth's major mountain ranges. This extreme age difference reflects the fundamental contrast in geological processes between the two planets. If viewed from a distance, the visual appearance of these mountains would differ dramatically as well. Earth's mountains typically have jagged, irregular profiles shaped by erosion and glaciation. Olympus Mons, with minimal erosion, maintains a smooth, dome-like appearance more reminiscent of a shield than a typical mountain. Its profile would appear less dramatic from ground level due to its gradual slopes, despite its immense height. The size comparison between Olympus Mons and Earth's mountains serves as a humbling reminder of how planetary conditions can produce wildly different outcomes from similar geological processes. While we rightfully marvel at Earth's impressive peaks, they represent just one expression of what mountains can be in our solar system, a small sample in a vast spectrum of planetary landforms that challenge our imagination and expand our understanding of geology beyond Earth. The remarkable scale of Olympus Mons compared to Earth's mountains reflects not just a difference in size, but also in longevity and eruptive history. While terrestrial volcanoes typically remain active for relatively brief geological periods, Olympus Mons tells a story of volcanic persistence spanning billions of years of Martian history. The eruptive chronology of Olympus Mons begins in Mars' distant past, approximately 3 billion years ago during what planetary geologists call the Hesperian period. This era marked a significant transition in Martian history, as the planet was shifting from its warmer, wetter early phase toward the colder, drier world we observe today. The earliest eruptions that would eventually form Olympus Mons likely emerged from fractures in the Martian crust, allowing magma from deep within the planet to reach the surface. These initial eruptions established the foundation upon which the enormous volcano would gradually build. Analysis of the lava flow patterns visible on the lower flanks suggests these early eruptions were characterized by highly fluid basaltic lava, similar in composition to what we see in Hawaii's volcanoes but on a much grander scale. The low viscosity of this lava allowed it to travel great distances before cooling and solidifying, helping to create the volcano's distinctive, gently sloped shield shape from the very beginning. During the subsequent Amazonian period, the most recent and longest Martian geological epoch, Olympus Mons entered its main constructive phase. Throughout this period, which began approximately 3 billion years ago and continues to the present day, the volcano experienced numerous eruptive episodes. Each episode might have lasted thousands or even millions of years, separated by periods of relative dormancy. This pattern of episodic activity is visible in the layered structure of the volcano, where scientists can identify distinct sets of lava flows representing different eruptive phases. One of the most fascinating aspects of studying Olympus Mons' eruptive history comes from crater counting, a technique that uses the number of impact craters on a surface to estimate its age. Younger surfaces have fewer craters, while older ones show more evidence of meteorite impacts. This method has revealed something remarkable. Some areas on Olympus Mons appear to be surprisingly young in geological terms, with certain lava flows estimated to be only about 200 million years old or even younger. This suggests that while the volcano began forming billions of years ago, it remained active for much of Martian history, with some of its final eruptive phases occurring relatively recently. The caldera complex at the summit tells its own story about the later stages of the volcano's evolution. The overlapping depressions that form this complex weren't created simultaneously, but instead represent a series of collapse events. When a volcanic eruption empties or partially empties the magma chamber beneath a volcano, the unsupported surface can collapse inward, creating a caldera. The presence of at least 6 overlapping calderas at the summit of Olympus Mons indicates that the volcano experienced multiple cycles of magma chamber filling and emptying during its later active phases. By examining the sequence of these caldera formations, scientists have determined that the volcanic activity gradually migrated over time. The oldest calderas appear in the northwestern portion of the summit complex, while the youngest are found in the southeast, suggesting a slow shift in the main eruptive centre over millions of years. Each of these major caldera-forming events would have been spectacular, releasing enormous volumes of lava and volcanic gases into the Martian environment. The eruptive style of Olympus Mons differs significantly from many of Earth's most famous volcanoes. While volcanoes like Mount St. Helens or Mount Vesuvius are known for their explosive eruptions that send ash and debris high into the atmosphere, Olympus Mons primarily produced effusive eruptions, characterized by relatively quiet outpourings of fluid lava. This difference relates partly to the composition of the magma and partly to Mars' lower gravity and atmospheric pressure, which affect how gases behave within the rising magma. During its most active periods, lava fountains may have erupted from the main vent, sending molten rock tens or hundreds of meters into the Martian sky before falling back to form rivers of lava that extended down the volcano's flanks. These lava flows created the distinctive pattern of ridges and channels still visible on the surface today. Some individual flows travelled hundreds of kilometers from their source, gradually building up the volcano's enormous bulk layer by layer. As the main summit vent occasionally became blocked, or as magma found easier paths to the surface, parasitic vents and flank eruptions appeared on the sides of the growing volcano. These secondary eruption sites created smaller cones and additional lava flows that contributed to the mountain's complex surface texture. Evidence of these flank eruptions is particularly visible on the northwestern and southeastern slopes, where chains of smaller vents follow fracture lines in the volcano's structure. The later stages of Olympus Mons' eruptive history show a general trend toward decreasing activity. As Mars's interior cooled over billions of years, the supply of magma gradually diminished, leading to less frequent and less voluminous eruptions. The youngest lava flows appear to have originated primarily from flank vents rather than the main summit, suggesting that the central magma system had begun to wane while satellite magma pathways remained temporarily viable. The question of whether Olympus Mons is truly extinct or merely dormant remains open. Given the evidence of geologically recent activity and the extremely long time span over which the volcano has operated, some scientists speculate that magma might still exist deep beneath the mountain, perhaps to emerge again in the distant future. However, without direct measurement equipment on the volcano itself, determining its current internal state remains challenging. Understanding the eruptive chronology of Olympus Mons provides crucial insights not just into the volcano itself, but into Mars's broader geological evolution. The gases released during billions of years of eruptions contributed significantly to the planet's atmosphere, potentially creating temporary climate conditions quite different from what we observe today. Similarly, the timing of major eruptive phases may correlate with other significant events in Martian history, such as changes in the planet's axial tilt or periods of glacial activity. Transitioning our view from the volcano's long eruptive history to the environment surrounding its base reveals an equally fascinating story. The base of Olympus Mons presents one of the most striking landscape features on Mars, a massive cliff formation that encircles much of the volcano like a giant natural wall. This escarpment is truly enormous, reaching heights of up to 6 kilometers in some sections, taller than the north face of Mount Everest from base to summit. Standing at the foot of these cliffs would be an overwhelming experience, with the rock face extending upward almost beyond what the human eye could take in from a single vantage point. The origin of this remarkable feature has been the subject of considerable scientific debate, with several competing theories attempting to explain its formation. One leading hypothesis suggests that the escarpment formed through massive landslides as the edges of the volcano collapsed under their own weight. Evidence for this comes from the enormous debris fields visible beyond the cliffs, which extend outward for tens of kilometers in some areas. These debris fields contain jumbled blocks of material that appear to have broken off from the main volcano structure and tumbled outward in massive avalanche events that would have been catastrophic in scale. Another theory proposes that the escarpment might have been carved by ancient Martian oceans that once lapped against the flanks of the growing volcano. According to this view, wave action could have eroded the base of Olympus Mons, creating steep cliffs similar to how coastal erosion creates sea cliffs on Earth. Supporting this hypothesis is the observation that the escarpment is most prominent on the northwestern side of the volcano, which faces toward the northern lowlands, where evidence suggests oceans might once have existed. A third explanation involves tectonic processes. The immense weight of Olympus Mons caused the Martian crust to bend downward beneath it. This flexure created stress patterns that may have resulted in faulting around the volcano's periphery, potentially contributing to the formation of the escarpment. The presence of fracture systems that roughly parallel the base of the volcano lends credence to this idea. The environment at the base of Olympus Mons differs notably from conditions higher up on the mountain. The atmospheric pressure, while still extremely low by Earth standards, is relatively higher at the base than at the summit. In fact, the pressure difference between the base and summit of Olympus Mons is greater than the entire range of atmospheric pressures found on Earth, from sea level to the summit of Mount Everest level to the top of Mount Everest. This gradient creates unique weather patterns as air masses move up and down the volcano's slopes. Temperature variations at the base also follow distinctive patterns. During the Martian day, sunlight warms the dark volcanic rocks, creating local heating effects. At night, temperatures plummet rapidly due to Mars' thin atmosphere, which cannot retain heat effectively. This daily temperature cycle causes rocks to expand and contract, contributing to a slow form of weathering that gradually breaks down the volcanic materials over time. The plains surrounding the base of Olympus Mons feature extensive lava fields that extend for hundreds of kilometers beyond the main volcano structure. These apron regions consist of overlapping lava flows that erupted from Olympus Mons throughout its history, creating a complex landscape of ridges, channels, and solidified lava pools. Some individual flows can be traced for over 200 kilometers from their source, demonstrating the extraordinary fluidity of the lava and the minimal erosion that has occurred since their formation. Particularly interesting features found at the base of Olympus Mons are the numerous lava tubes and collapsed lava channels. Lava tubes form when the surface of a flowing lava river cools and hardens while the interior continues to flow. When the eruption ends, the lava drains out, leaving behind a hollow tunnel. On Mars, these tubes can reach enormous dimensions. Some appear to be tens of meters in width and may extend for kilometers in length. Where the roofs of these tubes have collapsed, they create distinctive chains of pit craters that snake across the landscape. These lava tubes have attracted particular interest as potential sites for future human exploration or even habitation. The tubes would provide natural radiation shielding from Mars's harsh surface conditions, as well as insulation against the extreme temperature variations of the Martian day-night cycle. Some scientists have proposed that these structures could potentially host simple microbial life if it ever existed on Mars, as they would provide more protected environments than the exposed surface. Wind patterns around the base of Olympus Mons are influenced by the mountain's enormous bulk. As the thin Martian atmosphere flows around this massive obstacle, it creates distinctive circulation patterns that affect how dust and sand are transported and deposited. Dark streaks visible in orbital images show where winds have either scoured away light-coloured dust or deposited darker materials, creating elegant patterns that change seasonally as wind directions shift with Mars' orbital cycle. Evidence of possible water-lava interactions appears in several locations around the base of Olympus Mons. When hot lava encounters ice or water-saturated ground, it can create distinctive volcanic landforms called rootless cones or pseudocraters. These features form not from direct volcanic activity, but from explosive steam generation when lava heats subsurface water. The presence of these features suggests that at certain points in Martian history, the eruptions from Olympus Mons encountered ground ice or perhaps even liquid water, creating localized steam explosions that left their mark on the landscape. the gravitational signature around Olympus Mons reveals another fascinating aspect of its basal environment. Precise measurements from orbiting spacecraft show that the immense weight of the volcano has compressed the crust beneath it, creating what geologists call an isostatic depression. This depression is masked by the mountain itself, but extends beyond its visible base, affecting the broader regional topography and potentially influencing groundwater movement and subsurface ice distribution. While the base of Olympus Mons offers fascinating insights into the volcano's history and interaction with the surrounding Martian landscape, conditions at the summit present an entirely different environment, one of the most extreme on Mars. The summit of Olympus Mons rises 25 kilometers above the surrounding plains, placing it well above most of the already thin Martian atmosphere. This extreme altitude creates a set of conditions unlike anywhere else in our solar system, combining the challenges of high mountains, alien atmosphere, and extreme isolation. The atmospheric pressure at the summit of Olympus Mons is remarkably low, even by Martian standards. While the average surface pressure on Mars is only about 0.6% of Earth's sea level pressure, the summit of Olympus Mons experiences pressure less than 1/10 of that value. This means the air at the top of this Martian giant is more than 1,000 times thinner than what we breathe on Earth. In such conditions, water would instantly boil even at freezing temperatures, and traditional spacesuits would need significant reinforcement to prevent dangerous expansion. Temperature fluctuations at the summit are extreme and rapid. During daylight hours, the thin atmosphere allows intense solar radiation to directly heat the surface rocks to temperatures that might reach a relatively mild -20 degrees Celsius. However, as soon as the sun sets, this heat radiates quickly into space with almost no atmospheric insulation to retain it. Nighttime temperatures plummet to an astonishing -140 degrees Celsius or lower. This daily temperature swing of potentially more than 120 degrees Celsius would create tremendous thermal stress on any materials, natural or human-made, at the summit. The radiation environment at the top of Olympus Mons presents another significant challenge. Mars lacks the protective magnetic field that shields Earth from cosmic radiation and solar particles. This exposure is even more pronounced at the summit of Olympus Mons, where the already minimal atmospheric protection is further reduced. Any future human explorers would face radiation doses significantly higher than those experienced at Mars' average surface level, requiring additional shielding in habitats and spacesuits. The summit caldera complex itself spans approximately 80 kilometers across and consists of at least 6 overlapping depressions. These nested craters formed when the magma chamber beneath the volcano partially emptied during major eruptions, causing the unsupported surface to collapse inward. The deepest parts of the caldera complex drop about 3 kilometers below the caldera rim, creating a vast, relatively flat-floored basin surrounded by steep walls. Standing on the caldera floor would be like finding yourself in a giant stadium where the seats are kilometer-high cliffs and the playing field spans dozens of kilometers. The texture of the summit surface varies considerably across the caldera complex. Some areas display relatively smooth plains created by the last lava flows to flood the caldera floor before activity ceased. Other regions show rougher terrain with blocky fragments that broke off from the caldera walls during collapse events. Fractures and faults crisscross the caldera floor, evidence of continued settling and adjustment after the main collapse events. In certain locations, smaller vents and cones dot the surface, representing the final gasps of volcanic activity as magma found its way through cracks in the solidifying crust. From a vantage point on the rim of the summit caldera, the view would be truly otherworldly. On clear days, the curvature of Mars would be visible, with the horizon noticeably more curved than what we're accustomed to on Earth due to Mars's smaller size. Theoretical visibility from this height could extend more than 400 kilometers in all directions, though frequent dust in the Martian atmosphere would usually limit actual visibility. Looking outward, The vast plains surrounding Olympus Mons would stretch to the horizon, while looking inward would reveal the enormous expanse of the caldera complex below. Weather at the summit follows patterns unlike those anywhere else on Mars. The massive bulk of the mountain creates its own weather system, influencing how winds flow around and over it. As the thin Martian air is forced upward by the mountain, it cools and can sometimes form thin clouds of carbon dioxide or water ice crystals. These clouds occasionally create a cap that sits atop the volcano, visible from orbit. During dust storm season, the summit may emerge above the global dust layer like an island rising from a tan-coloured sea, while at other times it might be completely obscured by swirling dust clouds. One fascinating aspect of the summit environment relates to gravity. The immense mass of Olympus Mons actually increases the local gravitational pull slightly compared to the Martian average. However, this effect is more than offset by the increased distance from Mars's centre due to the extreme height of the mountain. The result is that gravity at the summit is measurably lower than at the base, about 3% less. Combined with Mars's already reduced gravity, about 38% of Earth's, a person standing on the summit would experience only about 37% of Earth's gravitational pull. Wind patterns at the summit can be surprisingly intense despite the thin atmosphere. The steep temperature gradients between day and night create pressure differences that drive winds up and down the mountain slopes. These katabatic winds, flowing downhill as cooled air seeks lower elevations, can reach speeds of several dozen meters per second, despite the low atmospheric density. These winds carry sufficient force to move dust and small particles, gradually eroding exposed rock faces and creating drift patterns around obstacles. The physical challenges of reaching the summit would be enormous for human explorers. The journey from base to peak would cover hundreds of kilometers of terrain, with gradually decreasing atmospheric pressure requiring carefully managed acclimatization protocols, not unlike how mountain climbers on Earth must adjust to high altitudes, but with even more extreme conditions. The thin atmosphere would provide minimal protection from micrometeorites, which regularly pepper the Martian surface. At the summit, these tiny space rocks would strike with nearly their full cosmic velocity, potentially creating hazards for exposed equipment and habitats. Despite these challenges, the scientific value of the summit region is immense. The caldera complex offers a natural cross-section of the volcano's upper layers, potentially revealing details about the final stages of its eruptive history. Samples collected from different portions of the caldera walls could provide a chronological record of how the volcano's magma composition changed over time. Additionally, any gases still seeping from fractures in the caldera floor might offer clues about current conditions deep within Mars, including whether any magmatic systems remain partially active. This extraordinary environment at the summit of Olympus Mons leads to a fundamental question. Why did this volcano grow to such enormous proportions, dwarfing anything found on Earth? Several interconnected factors contributed to the extraordinary size of Olympus Mons, each playing a crucial role in allowing this Martian wonder to reach its record-breaking dimensions. The most significant factor behind Olympus Mons' tremendous size is Mars' lack of active plate tectonics. On Earth, the crust is divided into moving plates that constantly shift position, recycling old crust back into the mantle through subduction zones while creating new crust at mid-ocean ridges. This means that when volcanic hotspots form on Earth, the crust above them eventually moves away, creating chains of volcanoes like the Hawaiian Islands rather than allowing a single volcano to grow continuously. Mars, however, has had a relatively stable crust for billions of years, with no significant plate movement. This stability allowed the hotspot that created Olympus Mons to remain in the same location, continuously feeding magma to the same edifice for potentially more than 3 billion years. The structure of the Martian lithosphere, the rigid outer layer that includes the crust and uppermost mantle, also contributed significantly to the volcano's growth. Mars' lithosphere is estimated to be much thicker than Earth's, perhaps 100 kilometers or more in depth. This thick, rigid layer was strong enough to support the enormous weight of Olympus Mons without breaking or subducting. On Earth, the weight of much smaller volcanoes like Hawaii's Mauna Loa actually causes the oceanic crust to bend downward. While Olympus Mons did create a depression in the Martian crust, the thicker lithosphere prevented catastrophic failure that might have limited its growth. Mars's lower surface gravity played another crucial role in allowing Olympus Mons to reach such heights. The gravitational pull at the Martian surface is only about 38% of Earth's. This reduced gravity means that volcanic structures on Mars can grow about 2.5 times taller than equivalent structures on Earth before their own weight causes them to collapse or spread laterally. The combination of lower gravity and stronger crust created perfect conditions for extreme vertical growth. The composition and viscosity of Martian magma contributed significantly to the volcano's extensive spread as well as its height. Analysis of Martian meteorites and remote sensing data suggests that Martian basaltic lavas were likely more fluid than many Earth equivalents, possibly due to higher iron content. More fluid lava can travel greater distances before cooling and solidifying, allowing for the creation of the extensive, gradually sloped shield structure that characterizes Olympus Mons. These far-flowing lavas built up layer by layer over time, extending the volcano's base while simultaneously adding to its height. The superplume theory offers another explanation for Olympus Mons' extraordinary size. According to this model, an unusually strong and persistent mantle plume, a rising current of hot material from deep within Mars, provided an exceptionally long-lived and voluminous magma source. On Earth, mantle plumes are relatively common, creating hotspot volcanoes like those in Hawaii, Iceland, Dot, and Yellowstone. However, Earth's more active interior tends to disrupt or weaken plumes over time. Mars's less dynamic interior may have allowed an exceptionally strong plume to persist without significant disruption for billions of years. The regional context of Olympus Mons within the Tharsis Bulge also contributed to its extreme height. The Tharsis region is an enormous volcanic plateau that rises several kilometers above the surrounding Martian landscape and stretches over thousands of kilometers. This entire region represents a massive upwelling of material from the Martian interior, essentially raising the ground floor from which Olympus Mons began its growth. The volcano's true height from base to summit is actually somewhat less than its 25-kilometer elevation above the reference level of Mars. But the Tharsis uplift allowed it to reach this extreme elevation relative to the rest of the planet. Scientists believe that cyclic patterns of volcanic activity may have characterized Olympus Mons' growth, rather than continuous eruption. The volcano likely experienced pulses of intense activity separated by periods of relative quiescence. These cycles might correlate with deeper processes within Mars, such as changes in mantle convection patterns or periodic buildup and release of heat. Each active cycle would add new layers to the growing volcano, with the longest and most recent active phases creating the surface features we observe today. The lack of significant erosion on Mars compared to Earth also allowed Olympus Mons to retain its size once built. Earth's mountains and volcanoes are constantly being worn down by water, ice, and wind. Mars has lacked liquid water on its surface for most of its history, has no glaciers to carve away at mountains, and its thin atmosphere produces less powerful erosive forces. This minimal erosion meant that once Olympus Mons formed, it remained largely intact rather than being gradually reduced in size, as would happen on Earth. The combination of all these factors, stable crust, thick lithosphere, low gravity, fluid lava, persistent mantle plume, regional uplift, cyclic activity, and minimal erosion, created the perfect conditions for building the largest volcano known in our solar system. Olympus Mons stands as testimony to how planetary conditions can dramatically affect geological processes, creating features that defy Earth-based expectations and expand our understanding of what's possible in our solar system. The extraordinary size of Olympus Mons and the unique conditions that allowed for its formation make it a compelling target for future exploration. However, The same features that make it scientifically valuable also create enormous challenges for human explorers hoping to study this Martian wonder up close. The sheer scale of the mountain presents logistical hurdles unlike anything faced in previous planetary exploration efforts. The most obvious challenge is the vast distance that would need to be covered to explore Olympus Mons thoroughly. With a base diameter of approximately 600 kilometers, traversing from one side of the volcano to the other would be equivalent to driving from San Francisco to Los Angeles. Even with advanced rovers moving significantly faster than current Martian vehicles like Perseverance, which typically covers less than 200 meters per day, a complete crossing could take months. Ascending from base to summit would require travelling hundreds of kilometers up an inclined slope, a journey that would likely take weeks even with specialized vehicles. This vast scale creates immediate problems for mission planning and resource allocation. Any expedition to explore Olympus Mons would require extraordinary endurance from both equipment and crew. Vehicles would need fuel or power supplies sufficient for months of continuous operation, far beyond what current Mars rovers carry. For human explorers, this would mean bringing enough oxygen, food, water, and other consumables for an extended journey, significantly increasing mission mass and complexity. Alternatively, multiple supply caches would need to be established along planned exploration routes, requiring additional preparatory missions. The variable atmospheric conditions across Olympus Mons create another layer of technical challenges. As explorers ascend the mountain, they would experience a gradual but significant decrease in atmospheric pressure from the already thin Martian baseline to conditions nearly approaching vacuum at the summit. This pressure gradient would require either pressurized vehicles capable of operating across this entire range or different vehicles specialized for different elevation zones. Spacesuits designed for surface operations at lower elevations might not be suitable for use near the summit without modification. Temperature variations across Olympus Mons would similarly stress equipment and life support systems. While the typical day-night temperature swing on Mars is already extreme compared to Earth, the summit experiences even more dramatic fluctuations, with nighttime temperatures potentially dropping below negative 140 degrees Celsius. Any vehicles or habitats would need robust thermal management systems capable of maintaining operational temperatures despite these extremes. Power systems relying on batteries would see their efficiency severely reduced in the extreme cold, while solar panels would generate less power in the thin, high-altitude atmosphere. Radiation exposure represents one of the most significant health concerns for human explorers on Olympus Mons. Mars lacks the protective magnetic field that shields Earth from cosmic radiation, and the thin atmosphere provides minimal additional protection. This radiation exposure becomes even more severe at higher elevations, where the already minimal atmospheric shielding is further reduced. Explorers at the summit could face radiation doses significantly higher than those experienced at Mars' average surface level, potentially limiting the safe duration of high-altitude excursions and requiring additional shielding in vehicles and habitats. The steep scarps around portions of Olympus Mons' base present their own exploration challenges. These cliffs, reaching heights of up to 6 kilometers in some areas, would be extremely difficult to ascend with wheeled or even tracked vehicles. While the overall slope of the volcano is gentle, these localized steep areas might require specialized climbing equipment or force explorers to take much longer routes to reach certain areas. The loose, potentially unstable material making up these scarps also presents landslide risks that would need careful evaluation before human missions. Communication would become increasingly difficult as explorers move across Olympus Mons. The massive bulk of the mountain could block direct line-of-sight transmissions to base stations or orbiting relays, potentially creating communication dead zones unless a comprehensive network of relay stations were established. The extreme environments at higher elevations could also affect the performance of communication equipment, requiring more robust systems than those used for standard Martian surface operations. One of the most underappreciated challenges would be the psychological impact of exploring such an enormous feature. Human explorers accustomed to Earth environments might find the scale of Olympus Mons disorienting. The combination of the mountain's vast size, the alien landscape, and the curved horizon visible from higher elevations, made more apparent by Mars' smaller diameter, could contribute to a sense of isolation beyond even that normally experienced during space missions. Maintaining crew mental health during months-long expeditions across this landscape would require careful consideration during mission planning. Dust storms present another significant hazard for Olympus Mons exploration. Mars experiences both local and global dust storms, with global events sometimes obscuring the entire planet for months. These storms could strand exploration teams with zero visibility, interfere with solar power generation, and cause damage to equipment through dust infiltration. While the summit might sometimes rise above global dust storms, teams caught at lower elevations during such events might be immobilized for extended periods, requiring sufficient supplies and shelter to weather these conditions. The potential for currently unknown geological hazards cannot be overlooked. While Olympus Mons is generally considered dormant, our understanding of its current state is based entirely on remote observations. Localized geothermal activity, unstable surfaces, gas emissions, or other hazards might exist that are not detectable from orbit. The first explorers would need to proceed with caution, continuously monitoring for signs of potential danger as they venture into areas never directly observed at ground level. Despite these formidable challenges, the scientific value of exploring Olympus Mons directly would be immense. The mountain stands as one of the most extraordinary geological features in our solar system, and studying it up close would revolutionize our understanding of planetary volcanism and Mars's internal evolution. The scientific implications of Olympus Mons extend far beyond the mountain itself, offering insights into fundamental planetary processes that have shaped worlds throughout our solar system. Perhaps the most significant scientific implication of Olympus Mons is what it reveals about the fundamental differences in geological evolution between Mars and Earth. The very existence of such an enormous volcano challenges early models of planetary development that were based primarily on Earth observations. Olympus Mons demonstrates that without plate tectonics, volcanic activity on a rocky planet follows dramatically different patterns, potentially concentrating in specific regions for billions of years rather than creating the distributed volcanic patterns seen on Earth. This insight forces planetary scientists to reconsider how volcanic processes might operate on other worlds with different internal structures and evolutionary histories. The lessons from Olympus Mons have been applied to understanding features on Venus, where enormous shield volcanoes also exist, and even to interpreting volcanic features on large moons like Jupiter's Io, the most volcanically active body in our solar system. By understanding the conditions that allowed Olympus Mons to form, we gain a framework for analysing volcanic processes across the solar system. The long-term volcanic activity at Olympus Mons also provides crucial information about Mars' interior structure and thermal history. The volcano's extended period of activity, potentially spanning billions of years with the most recent eruptions possibly occurring just millions of years ago, indicates that Mars's interior remained hot enough to generate magma for much longer than previously thought. This challenges earlier models that suggested Mars cooled quickly due to its smaller size relative to Earth. By studying the composition of lava flows from different periods of Olympus Mons development, scientists can track changes in the Martian mantle over time. Early flows likely tapped different magma sources than later eruptions, potentially recording chemical changes as the planet's interior evolved. This stratigraphic record essentially serves as a core sample of Mars's mantle at different points in its history, offering insights that would be difficult or impossible to obtain otherwise. Olympus Mons also plays a crucial role in understanding Mars's climate history. The gases released during its eruptions, particularly water vapor and carbon dioxide, contributed significantly to the planet's atmosphere throughout its history. By determining the timing and volume of major eruptive phases, scientists can better estimate how volcanic activity influenced Martian climate conditions, potentially creating warmer, wetter periods during intense eruptions before returning to colder, drier conditions during dormant phases. The physical structure of Olympus Mons itself contains valuable scientific information. The patterns of lava flows visible on its slopes reveal how volcanic material behaves under Martian conditions, information that helps calibrate computer models of volcanic processes under different gravitational and atmospheric conditions. The caldera complex at the summit tells a story of magma chamber processes occurring deep within the Martian crust, while fault patterns on the volcano's flanks reveal how such an enormous structure deforms under its own weight. From a comparative planetology perspective, Olympus Mons serves as an important end-member example of what volcanic processes can produce. Earth's plate tectonics prevents individual volcanoes from growing beyond certain limits, while Venus's extreme surface conditions create different volcanic morphologies. Olympus Mons shows us what happens when volcanism continues uninterrupted at one location for billions of years on a planet with moderate gravity and no plate movement, a scenario not found on our home planet but potentially common on other rocky worlds throughout the galaxy. The relationship between Olympus Mons and the surrounding Tharsis region provides insights into how concentrated volcanic activity can reshape an entire hemisphere of a planet. The massive weight of the Tharsis volcanic province, of which Olympus Mons is the most spectacular feature, actually caused Mars's crust to tilt, potentially altering the planet's rotational axis over geological time. This demonstrates how internal geological processes can have planet-wide effects, influencing climate patterns, water distribution, and other surface conditions. For astrobiologists, Olympus Mons has additional significance related to Mars' potential habitability. The long-term volcanic activity would have released not just greenhouse gases, but also water vapour and potentially other compounds necessary for life. Localized hydrothermal systems might have existed where magma interacted with subsurface ice or water, creating environments that could have been habitable for heat-loving microorganisms similar to those found in volcanic regions on Earth. The timing of Olympus Mons' active phases might correlate with periods when surface conditions on Mars were more conducive to life. The layered structure of Olympus Mons also provides a unique chronological record of Mars's history. Each layer represents material deposited during a specific time period, potentially preserving evidence of atmospheric conditions, impact events, and other environmental factors contemporary with that eruption. By studying these layers in sequence, scientists could reconstruct a detailed timeline of Martian environmental conditions spanning billions of years, a record unlike anything available on the more geologically active Earth. While Olympus Mons serves as a remarkable scientific record and has profound implications for our understanding of planetary evolution, the human story of its discovery and observation is equally fascinating. Unlike many of Earth's most prominent geographical features, which have been known to humanity for our entire recorded history, Olympus Mons remained completely unknown until relatively recent times, hidden from view on our neighbouring planet until technological advancements allowed us to glimpse it. The first hints of Olympus Mons' existence came in the late 19th century, though no one at the time realised what they were actually seeing. When observing Mars through early telescopes, astronomers occasionally noted a bright spot in the Tharsis region that appeared to stand out from its surroundings. This feature was given the name Nix Olympica, meaning snows of Olympus, because early observers thought they might be seeing a snow-capped mountain similar to those on Earth. In reality, what they were likely observing was high-altitude clouds forming over the massive volcano, a phenomenon that still occurs today. However, these early observations provided very little detail. The limitations of 19th and early 20th century telescopes meant that even the best Earth-based observations showed Mars as little more than a reddish disk with some darker and lighter patches. The true nature of Nix Olympica remained speculative. with many astronomers doubting it represented a mountain at all. Some alternative theories suggested it might be a bright desert region or even a patch of vegetation. Remember that until the mid-20th century, the idea of canals and vegetation on Mars remained popular in both scientific and public imagination. The first major breakthrough in understanding Olympus Mons came with the Mariner missions, particularly Mariner 9, which reached Mars in 1971. When Mariner 9 arrived at Mars, the planet was engulfed in a global dust storm that obscured nearly all surface features. As the spacecraft orbited and the storm gradually cleared, the first features to become visible were several dark spots poking above the dust clouds. These spots turned out to be the tops of enormous volcanoes, with Olympus Mons the largest among them. The timing of Mariner 9's arrival during this dust storm was a stroke of scientific luck. By seeing these volcanic peaks emerging from the dust while everything else remained hidden, scientists immediately realized they were observing mountains of extraordinary height. When the dust finally settled, Mariner 9 was able to photograph Olympus Mons in its entirety, revealing for the first time the true scale and shape of this colossal feature. It was at this point that scientists realized Nix Olympica was not just a mountain, but the largest volcano in the solar system. The name was officially changed from Nix Olympica to Olympus Mons at this time, maintaining the connection to Mount Olympus of Greek mythology, the home of the gods, but correctly identifying it as a mountain, Mons, rather than a snowy region, Nix. The first complete images from Mariner 9 stunned the scientific community. Here was a volcanic feature that dwarfed anything known on Earth, challenging existing models of volcanic formation and planetary geology. The Viking missions of the 1970s provided the next major advance in our understanding of Olympus Mons. Viking 1 and 2 both entered orbit around Mars in 1976, carrying improved cameras that could resolve features as small as 40 meters across. These missions produced much more detailed images of Olympus Mons, revealing the complex caldera at its summit, the terrace slopes formed by lava flows, and the mysterious escarpment around its base. Viking data allowed scientists to make the first accurate measurements of the volcano's dimensions, confirming its status as the tallest mountain and largest volcano in the solar system. The Viking orbiters also carried infrared instruments that helped determine the composition of the volcanic material, confirming that Olympus Mons was built primarily from basaltic lava similar to that found in shield volcanoes on Earth, though with some compositional differences reflecting the unique Martian environment. A significant leap forward came in the 1990s with the Mars Global Surveyor mission, which carried a laser altimeter capable of precisely measuring elevations across the Martian surface. This instrument, called MOLA, Mars Orbiter Laser Altimeter, provided the first detailed topographic maps of Olympus Mons, revealing its true height of approximately 25 kilometers above the surrounding plains and its gentle average slope of only 5 degrees. MOLA data allowed scientists to create the first accurate three-dimensional models of the volcano, providing new insights into its formation and evolution. The early 21st century brought a fleet of increasingly sophisticated orbiters. The European Space Agency's Mars Express, arriving in 2003, carried a high-resolution stereo camera that produced stunning visual images of Olympus Mons and allowed creation of detailed perspective views that gave people on Earth their first realistic impression of what it might look like to fly over this Martian giant. NASA's Mars Reconnaissance Orbiter, reaching Mars in 2006, carried cameras capable of resolving features less than a meter across, revealing fine details of lava flows, channels, and collapse features that hadn't been visible in earlier missions. Throughout this progression of increasingly detailed observations, our understanding of Olympus Mons has evolved dramatically. Early simplistic views of a standard volcano, just bigger, gave way to recognition of its complex history and unique features. Scientists identified multiple caldera collapse events at the summit, traced individual lava flows extending for hundreds of kilometers, and recognized that the volcano had been active over an extraordinarily long period, with some areas potentially experiencing eruptions in the relatively recent geological past. Modern observation techniques now include not just visual imaging but spectroscopic analysis that can identify specific mineral compositions, ground-penetrating radar that can reveal structures below the surface, and thermal imaging that can detect subtle temperature variations across the volcano. These advanced techniques have transformed Olympus Mons from a distant, fuzzy spot in telescopes to one of the most thoroughly studied geological features beyond Earth. Yet, despite all this remote observation, no spacecraft has ever directly visited Olympus Mons' surface. All our knowledge comes from orbit, making it somewhat like studying Mount Everest exclusively from airplanes, detailed in some ways but missing the ground-level perspective. Future missions may eventually land near or even on this Martian giant, providing the close-up observations that would answer many remaining questions about its formation and history. The history of Olympus Mons observation mirrors the broader development of planetary science, from speculation based on limited data to detailed understanding based on increasingly sophisticated measurements. Each generation of Mars missions has revealed new aspects of this extraordinary feature, and undoubtedly future observations will continue to deepen our appreciation of the largest volcano in our solar system. The discovery and increasingly detailed observation of Olympus Mons naturally leads to a fundamental question. Why does Mars host volcanoes of such extraordinary size? The contrast between Martian volcanoes and their Earth counterparts is stark. Olympus Mons is roughly 3 times taller than Mount Everest and covers an area comparable to the entire state of Arizona. Understanding why Mars developed such enormous volcanic structures requires examining the fundamental geological differences between the two planets. The most significant factor behind Mars's giant volcanoes is the planet's lack of plate tectonics. Earth's crust is divided into plates that constantly move, driven by convection in the mantle below. When volcanic hotspots form on Earth, the moving crust above them means that the hotspot creates a series of volcanoes over time, rather than a single massive one. The Hawaiian island chain exemplifies this process, as the Pacific plate moves over a relatively fixed hotspot. A series of islands has formed over millions of years, each island representing a distinct volcano. Mars, in contrast, has a rigid, immobile crust. When a hotspot formed under what would become Olympus Mons, the crust remained fixed above it for billions of years. This allowed magma to reach the surface at the same location continuously, building the volcano ever higher and wider rather than creating a chain of separate volcanoes. It's somewhat like the difference between squeezing toothpaste onto a moving conveyor belt versus squeezing it onto a stationary surface. In the first case, you get a line of paste. In the second, you get a growing pile. The thickness of Mars' lithosphere, the rigid outer shell that includes the crust and uppermost mantle, also plays a crucial role. Mars' lithosphere is estimated to be about 100 to 150 kilometers thick, significantly thicker than Earth's average of about 100 kilometers. This thicker, stronger shell can support much larger volcanic structures without buckling or breaking under the weight. On Earth, the weight of even relatively modest-sized volcanoes can cause the crust to bend downward, while Olympus Mons has created some depression in the Martian crust. The thicker lithosphere prevented the kind of crustal failure that would limit growth on Earth. Mars's lower surface gravity, about 38% of Earth's, is another key factor. With lower gravity, rocks can be stacked higher before their own weight causes them to deform or collapse. This means that volcanic mountains on Mars can grow roughly 2.5 times taller than equivalent structures on Earth before reaching their stability limits. The combination of lower gravity and a thicker, stronger crust created ideal conditions for extreme volcanic growth. The composition of Martian magma also contributed to the formation of enormous shield volcanoes. Evidence suggests that Martian lava had lower viscosity than many Earth lavas. meaning it could flow more easily and spread out over greater distances before cooling and solidifying. This property allowed the creation of the extensive, gently sloped shield structure characteristic of Olympus Mons and other large Martian volcanoes. The more fluid nature of this lava may be related to its chemical composition, particularly its iron content and temperature. Water content in magma significantly affects volcanic eruption styles, and here too Mars and Earth differ substantially. Earth magmas often contain more water, which can create explosive eruptions as the water flashes to steam when pressure is released. Martian magmas appear to have been relatively dry, particularly in later periods of the planet's history, leading to less explosive, more effusive eruptions. These quieter eruptions are more conducive to building large shield volcanoes, as the material is deposited relatively gently rather than being violently ejected. The longevity of volcanic activity on Mars is another critical factor. Evidence suggests that volcanism at Olympus Mons may have been active, at least intermittently, for billions of years. This extraordinarily long eruption timeline, much longer than typical for Earth volcanoes, allowed for the accumulation of enormous volumes of material in one location. The most recent lava flows on parts of Olympus Mons might be just a few million years old, suggesting that the volcano remained active for most of Martian history. Mars's early volcanic history may have been particularly intense due to the rapid cooling of the planet. Being smaller than Earth, Mars lost heat more quickly, potentially leading to a period of substantial mantle melting and widespread volcanic activity as the planet's interior reorganized. This period could have established the large volcanic centers that later evolved into the massive shield volcanoes we see today. The regional context of Mars's giant volcanoes is also significant. Most of the largest volcanoes, including Olympus Mons, are clustered in the Tharsis region, a vast bulge in the Martian crust that rises several kilometers above the surrounding terrain and stretches over thousands of kilometers. This concentration suggests that this region experienced particularly intense upwelling from the Martian mantle, focusing volcanic activity in specific areas rather than distributing it globally as on Earth. The minimal erosion on Mars preserved volcanic structures once they formed. Earth's volcanoes are constantly being worn down by water, ice, and wind, with rainfall and glaciers carving into their flanks and gradually reducing their size. Mars has lacked liquid water on its surface for most of its history, has no glaciers to carve away at mountains, and its thin atmosphere produces less powerful erosive forces. Once Olympus Mons and its siblings formed, they remained largely intact rather than being gradually reduced in height, as would happen on Earth. Understanding why Mars developed such enormous volcanoes provides insights not just into Martian geology, but into fundamental planetary processes. The stark differences between Martian and Earth volcanoes highlight how varying conditions, different gravity, absence or presence of plate tectonics, composition of planetary crusts, and atmospheric conditions can produce dramatically different outcomes from similar underlying processes of mantle convection and magma generation. This comparative perspective enhances our understanding of how terrestrial planets evolve and the range of geological features they can develop. While the extraordinary size of Martian volcanoes results from a combination of planetary factors, understanding Olympus Mons properly requires looking beyond the volcano itself to the broader geological context in which it formed. Olympus Mons is not an isolated feature, but rather the most spectacular component of a vast volcanic region known as the Tharsis Province, one of the most extraordinary geological features in our solar system. The Tharsis region forms an enormous bulge on the Martian surface, rising several kilometers above the surrounding plains and stretching over roughly 5,000 kilometers, about a quarter of Mars' circumference. This immense plateau represents the largest volcanic province known in our solar system, containing approximately 30 million cubic kilometers of volcanic material. To put this in perspective, the entire volume would be enough to cover the United States in a layer approximately 3 kilometers thick. At the heart of the Tharsis region lie four massive shield volcanoes, Olympus Mons itself, along with what geologists call the Tharsis Montes, a nearly straight line of three enormous volcanoes named Olympus Mons, Pavonis Mons, and Asia Mons. While smaller than Olympus Mons, each of these three volcanoes would still dwarf anything on Earth, rising 15 to 18 kilometers above the surrounding plains and spanning hundreds of kilometers at their bases. The alignment of these three volcanoes along a northeast-southwest axis suggests they formed along a major crustal fracture zone where magma found easier paths to the surface. Olympus Mons sits slightly apart from this trio, positioned at the northwestern edge of the Tharsis Bulge. Its separate location may indicate that it formed from a distinct magma source, or perhaps represents a later stage in the region's volcanic evolution. The relationship between Olympus Mons and the three aligned volcanoes provides important clues about how magma moved through the Martian crust and how the internal plumbing of this vast volcanic system evolved over time. Beyond these giant shield volcanoes, the Tharsis region contains numerous smaller volcanic features that highlight the area's complex history. Alba Mons, formerly called Alba Patera, located north of Olympus Mons, has a much lower profile but spreads over an even larger area, making it potentially the most extensive volcano in the solar system by surface area, though not by height or volume. Hundreds of smaller volcanic domes, cones, and irregular volcanic features dot the Tharsis landscape, representing smaller eruptions that occurred throughout the region's long active history. The entire Tharsis Bulge is crisscrossed by an impressive network of fractures and graben, linear, trench-like features formed when the crust stretches and blocks of land drop downward between parallel faults. These fractures radiate outward from the central Tharsis region like spokes from a hub, extending thousands of kilometers across the Martian surface. Their pattern suggests they formed as the weight of the accumulating volcanic material caused the crust to bulge upward, creating tensional forces that cracked the surface in characteristic patterns. Perhaps the most spectacular fracture system associated with Tharsis is Valles Marineris, the enormous canyon system that stretches over 4,000 kilometers along the eastern edge of the Tharsis Bulge. While often compared to the Grand Canyon on Earth, Valles Marineris dwarfs its terrestrial counterpart, reaching depths of up to 7 kilometers and widths of up to 200 kilometers in places. Though water may have played a role in shaping parts of this canyon system, its primary origin appears to be tectonic, directly related to the stresses created by the Tharsis uplift. The Tharsis region began forming early in Martian history, with evidence suggesting volcanic activity started more than 3 billion years ago during the Noachian period. The bulk of the volcanic construction occurred during the subsequent Hesperian period, though activity continued well into the Amazonian period, the most recent era of Martian geological history. This extended period of activity makes Tharsis not just a geographical feature, but a chronicle of Mars' internal evolution, spanning most of the planet's history. The immense weight of the Tharsis Bulge affected Mars on a global scale. The concentration of so much mass in one region actually changed how the entire planet balanced, potentially causing a phenomenon called true polar wander, where the planet's crust and mantle shift relative to its rotational axis. Some scientists propose that this reorientation influenced Mars' climate history by changing the distribution of solar heating across its surface. The weight also caused the crust to bend downward beneath Tharsis, while creating a corresponding bulge on the opposite side of the planet, much like how pressing your finger into a balloon causes a bulge on the other side. The long-term volcanic activity in Tharsis played a crucial role in Mars's atmospheric evolution. Gases released during eruptions, particularly carbon dioxide and water vapor, contributed significantly to the Martian atmosphere throughout the planet's history. During the most active phases, these volcanic emissions may have temporarily thickened the atmosphere enough to allow warmer conditions and possibly even rainfall in some regions. Understanding the timing and intensity of Tharsis volcanism helps scientists reconstruct Mars's climate history and why it evolved from potentially habitable conditions to the cold, dry world we see today. groundwater systems were also influenced by Tharsis volcanism. The heat from magma chambers and volcanic activity would have warmed the subsurface, potentially creating hydrothermal systems where circulating hot water interacted with rocks, environments that on Earth often host specialized microbial ecosystems. Channel networks visible on Tharsis slopes suggest that subsurface water sometimes erupted as springs where it encountered magma, creating distinctive flow features. These water volcanic interactions make Tharsis particularly interesting from an astrobiological perspective. The Tharsis region essentially functions as a window into Mars' interior, telling us about the planet's thermal evolution, mantle composition, and how its crust responded to long-term volcanic activity. By studying variation in the composition of lava flows across the region and through time, scientists can track how the Martian mantle evolved chemically. The distribution and timing of volcanic centers reveal how heat flow within the planet changed as Mars cooled over billions of years, gradually shifting from widespread volcanic activity to increasingly concentrated centers. As our understanding of the broader Tharsis province has grown, so has our appreciation for Olympus Mons as part of this larger volcanic system rather than an isolated feature. The volcano's extraordinary size makes more sense when viewed as the culminating expression of processes that shaped an entire region of Mars over billions of years, processes that influenced the entire planet's evolution and potentially its habitability throughout its history. This comprehensive geological context not only enhances our understanding of how Olympus Mons formed, but also highlights the potential resources this massive volcano might offer to future explorers. As humanity looks toward eventual human missions to Mars, the possibility of utilizing local resources becomes increasingly important. And Olympus Mons contains a variety of potentially valuable materials that could support exploration and perhaps even settlement. The most obvious resource throughout Olympus Mons is the abundant basaltic rock that makes up the entire volcanic edifice. While ordinary rock might not seem immediately valuable, basalt has numerous practical applications for a Martian settlement. It can be processed into regolith cement for construction, melted and formed into bricks, slabs, or fibre strands, or even used as radiation shielding due to its good absorption properties. The composition of Martian basalts, rich in iron, magnesium, aluminum, and silicon, makes them potentially suitable for various manufacturing processes once properly refined. Iron is particularly abundant in Martian volcanic rocks, typically present at levels of 15 to 20% by weight as iron oxide. This concentration is higher than in many Earth basalts and represents a potential iron ore resource that could be extracted using relatively straightforward reduction processes. Indigenous iron production would be crucial for manufacturing structural components, tools, and machinery parts on Mars, reducing the mass that would need to be transported from Earth. Beyond basic construction materials, Olympus Mons likely contains a variety of useful mineral deposits formed through volcanic processes. Hydrothermal systems, where hot water circulates through rocks, often create concentrated deposits of minerals including sulfur compounds, various salts, and potentially even precious metals. On Earth, such hydrothermal deposits associated with volcanism are important sources of copper, zinc, gold, and silver. While the extent of hydrothermal activity on Olympus Mons remains uncertain, the long-term interaction between magma and groundwater would likely have created such mineral concentrations in some areas. Perhaps the most valuable resource on Mars for early explorers would be water, and Olympus Mons may contain significant water reserves in various forms. Ground-penetrating radar observations from Mars-orbiting spacecraft have detected what appear to be substantial ice deposits beneath the surface in many regions of Mars. The unique thermal environment of a massive volcano like Olympus Mons, with its history of heat flow from the interior, could create conditions where subsurface ice is concentrated in particular zones. Additionally, certain minerals formed in volcanic environments can contain water within their crystal structure. These hydrated minerals represent another potential water source that could be extracted through heating. The varying ages of different parts of Olympus Mons offer access to diverse materials from different periods in Martian history. The oldest exposed rocks, found in some of the deeper canyon walls and at the base of the escarpment, might date back more than 3 billion years, while the youngest lava flows could be just tens of millions of years old. This time, range provides a sampling of materials formed under different conditions throughout Mars's geological history, potentially including rare or useful compounds that formed only during specific periods. The structure of Olympus Mons provides natural shelters that future explorers might utilize. Lava tubes, underground tunnels formed when the outer layer of a lava flow cools while the interior continues to flow, are common features in shield volcanoes. On Mars, these tubes can reach enormous proportions, potentially extending for kilometers with heights and widths of tens of meters. These natural caverns would offer protection from radiation and extreme temperature fluctuations, making them attractive locations for habitats. Orbital imagery has identified numerous collapsed sections of lava tubes on Olympus Mons, suggesting an extensive network of these features throughout the volcano. The altitude gradient across Olympus Mons creates varied pressure and temperature environments that could be advantageous for different activities. Lower elevations with relatively higher atmospheric pressure might be more suitable for initial habitats and basic agriculture, requiring less structural reinforcement against the pressure differential. Meanwhile, the summit regions, with their near-vacuum conditions, might be ideal for certain scientific experiments, astronomical observations, or industrial processes that benefit from low-pressure environments. Geothermal energy represents another potential resource. While Olympus Mons is generally considered dormant rather than active, the immense size of the volcano suggests significant residual heat may still exist beneath the surface. Deep drilling might access thermal gradients that could be used for power generation or direct heating of habitats. Even modest temperature differences between the surface and subsurface could be exploited using appropriate heat pump technologies. If any regions of elevated heat flow still exist, perhaps associated with the most recent volcanic activity, these would be particularly valuable energy resources. The extensive lava flows that make up Olympus Mons are filled with voids, vesicles, and natural cavities formed as gases escaped from the cooling lava. These porous materials could serve various practical purposes, as natural insulation for habitats, as growing media for plants once appropriately prepared, or as substrates for microbial bioreactors producing food or other biological products. The varying porosity and structure of different lava flows would provide materials with different properties suitable for different applications. The unique environmental conditions at different elevations on Olympus Mons might also support specialized research or manufacturing processes. The thin atmosphere near the summit creates conditions where solar radiation reaches the surface with minimal filtering, potentially useful for solar power generation or certain photochemical industrial processes. The extreme cold at higher elevations, particularly during the Martian night, could be harnessed for cryogenic storage or processes requiring low temperatures without the energy cost of artificial cooling. From a long-term perspective, the geological diversity across Olympus Mons offers a natural laboratory for developing and testing various resource utilization techniques that could later be applied elsewhere on Mars or even other planetary bodies. The mountain's range of rock types, ages, structures, and environmental conditions concentrated in one region would allow systematic comparison of different extraction and processing methods under varying conditions, accelerating the development of effective resource utilization strategies for Mars exploration and settlement. While the potential resources of Olympus Mons offer exciting possibilities for future exploration, some of the most intriguing aspects of this enormous volcano remain its more mysterious features, particularly the massive cliff formations that encircle much of its base. These towering escarpments represent one of the most dramatic landscape features on Mars and have puzzled planetary scientists since they were first observed in detail by the Viking orbiters in the 1970s. The basal escarpment of Olympus Mons forms an irregular ring around much of the volcano's perimeter, creating what appears from orbit as a distinct boundary between the mountain and the surrounding plains. These cliffs are truly enormous, reaching heights of up to 6 kilometers in some sections, taller than the north face of Mount Everest from base to summit. If you were standing at the foot of these cliffs, they would rise almost vertically above you, extending so high that their tops might be obscured by clouds or haze. What makes these escarpments particularly intriguing is that they don't have obvious equivalents on Earth's volcanoes. While terrestrial volcanoes can develop cliff faces through various processes, nothing matches the scale and extent of the Olympus Mons escarpment. This uniqueness has led to several competing theories about how these massive cliffs formed, with scientists still debating which explanation best fits the evidence. One of the earliest and most persistent theories suggests the escarpment resulted from enormous landslides as the edges of the volcano collapsed under their own weight. According to this hypothesis, the outer portions of the volcano became unstable as it grew ever larger, eventually giving way in gigantic mass-wasting events. Supporting this idea are the vast debris fields visible extending outward from the base of the cliffs in many areas. These chaotic terrains contain enormous blocks and jumbled materials that appear to have broken away from the main volcanic structure and slid outward, sometimes travelling more than 100 kilometers from the mountain's base. Detailed imaging of these debris fields reveals features consistent with landslides, including elongated ridges parallel to the direction of movement and pressure ridges where flowing material piled up against obstacles. The scale of these potential landslides dwarfs any known on Earth. Some individual events may have involved hundreds of cubic kilometers of material moving as a semi-coherent mass. If this landslide theory is correct, these would represent some of the largest mass-wasting events ever identified in the solar system. A second major theory proposes that the escarpment formed through interaction with ancient Martian oceans. According to this hypothesis, during periods when large bodies of water existed in Mars's northern lowlands, these waters would have lapped against the northern and northwestern flanks of the growing Olympus Mons, creating coastal erosion similar to how sea cliffs form on Earth. The location and orientation of the most prominent sections of escarpment, particularly well developed on the northwestern side of the volcano facing the northern plains where evidence of ancient oceans is strongest, lends some support to this idea. If the ocean erosion theory is correct, the escarpment would represent a paleo shoreline, marking the boundary between land and sea during a critical phase of Martian history when the planet still had sufficient surface water to form large standing bodies. Proponents point to features resembling coastal landforms, including what appear to be wave-cut terraces at consistent elevations and potential beach deposits at the base of some cliff sections. However, the extreme height of the escarpment poses challenges for this theory, as it's difficult to explain how wave action alone could carve cliffs several kilometers high. A third explanation involves tectonic processes related to the enormous weight of Olympus Mons. As the volcano grew, its immense mass caused the Martian crust to bend downward beneath it. This flexure created stress patterns that may have resulted in major faulting around the volcano's periphery. According to this theory, the escarpment represents a series of thrust faults where sections of crust were pushed upward and over adjacent areas as the central portion sank under the volcano's weight. The roughly circular pattern of the escarpment aligns with what might be expected from such a process. Supporting the tectonic theory are observations of fracture systems that roughly parallel the escarpment in many areas, suggesting structural control of its formation. Additionally, some sections show features consistent with fault scarps, including relatively straight cliff faces and distinctive triangular facets characteristic of fault-controlled mountain fronts on Earth. Most planetary scientists now believe that the escarpment likely formed through some combination of these processes rather than any single mechanism. The northwestern sections might indeed show evidence of oceanic erosion, while other areas display clearer signs of landslides or faulting. The complexity of the escarpment structure suggests its formation history spanned hundreds of millions of years and involved multiple geological processes operating at different times and locations around the volcano's enormous circumference. Dating of the escarpment and associated features indicates it began forming at least 2 billion years ago, with different sections developing at different rates. Some portions appear relatively young, with minimal subsequent modification, while others show signs of extensive erosion and multiple episodes of collapse and retreat. This age variation suggests the processes forming the escarpment operated over an extended period rather than resulting from a single event or brief episode. One particularly intriguing aspect of the basal escarpment is evidence of interaction between volcanic activity and water or ice. In several locations, features resembling rootless cones or pseudo-craters appear near the base of the cliffs. These distinctive formations typically form when lava flows over water-saturated ground, causing steam explosions as the water flashes to vapor. Their presence suggests that, at times, lava flowing down from Olympus Mons encountered either standing bodies of water or ground ice at the volcano's base, creating explosive interactions that left lasting marks on the landscape. The escarpment also provides a unique cross-sectional view into the internal structure of Olympus Mons. The cliff faces expose layers of lava flows stacked one upon another, revealing the volcano's construction history in a way not possible on its gently sloping flanks. By studying these exposed layers, scientists can identify different eruption episodes, measure flow thicknesses, and potentially identify periods of dormancy represented by weathered horizons or sediment layers between lava flows. Recent high-resolution imaging of the escarpment has revealed additional complexities, including evidence of repeated cycles of collapse and subsequent volcanic burial. In some areas, older landslide deposits appear to have been covered by later lava flows that then experienced their own collapse events. This pattern suggests a dynamic interaction between constructive volcanic processes building the mountain and destructive collapse processes at its margins throughout much of its history. The escarpment also creates unique microclimates around Olympus Mons. The towering cliffs cast enormous shadows that can extend for tens of kilometers during morning and evening hours, creating temperature variations that drive local wind patterns. These cliff-influenced winds have sculpted distinctive erosion features on nearby plains and may contribute to the accumulation of dust deposits in certain sheltered areas at the volcano's base. Understanding the mysteries of Olympus Mons' basal escarpment remains an active area of research. Each new Mars orbiter with improved imaging capabilities reveals additional details that help refine theories about its formation. The complex history recorded in these enormous cliffs provides crucial insights not just into the evolution of Olympus Mons itself, but into broader questions about Martian geology, ancient water distribution, and how massive volcanic structures behave over billions of years of planetary evolution. The formation and evolution of Olympus Mons also played a crucial role in shaping Mars' atmosphere throughout the planet's history. As the largest volcano on Mars, and indeed in the entire solar system, Olympus Mons released enormous quantities of gases during its eruptive history, gases that significantly influenced the composition, density, and evolution of the Martian atmosphere we observe today. When Olympus Mons began forming more than 3 billion years ago, Mars was a very different world from the cold desert planet we now observe. Evidence suggests that early Mars had a thicker atmosphere and at least occasional surface water, creating conditions potentially suitable for simple life forms. The volcanic activity that built Olympus Mons and the broader Tharsis region played a major role in maintaining and modifying these conditions over time before they eventually gave way to the current thin, cold atmosphere. Each eruption of Olympus Mons released volcanic gases into the Martian environment, with carbon dioxide, water vapor, and sulfur compounds being the most significant. Carbon dioxide, a greenhouse gas, would have helped trap solar heat, potentially warming the Martian surface. Water vapor, another greenhouse gas, would have further enhanced this warming effect, while also providing a source of water that could condense as rain or snow under the right conditions. Sulfur dioxide and hydrogen sulfide would have created acidic conditions in the atmosphere and, when combined with water, potentially on the surface as well. The total volume of gases released by Olympus Mons over its active lifetime is staggering. Based on its size and the typical gas content of basaltic magmas, scientists estimate that Olympus Mons alone may have released enough carbon dioxide to create an atmosphere with pressure several times higher than Mars' current atmosphere, at least temporarily. When combined with emissions from other volcanoes in the Tharsis region and elsewhere on Mars, volcanic activity likely produced enough gas to sustain a moderately thick atmosphere for extended periods. However, these volcanic contributions to the atmosphere weren't permanent. Mars lacks Earth's self-regulating carbon cycle, where carbon dioxide is continuously recycled between atmosphere, oceans, and rocks. On Mars, atmospheric gases faced several removal processes. The planet's low gravity, about 38% of Earth's, means it has less ability to hold onto its atmosphere against the pressure of solar radiation. Additionally, Mars lost its global magnetic field early in its history, leaving its atmosphere vulnerable to being stripped away by the solar wind, the stream of charged particles continuously flowing from the Sun. This atmospheric loss created a complex relationship between volcanic activity and atmospheric conditions. During periods of intense volcanism, when Olympus Mons and other volcanoes were highly active, they could replenish atmospheric gases faster than they were being lost to space, potentially maintaining relatively warm, dense atmospheric conditions. During volcanic lulls, atmospheric loss would gradually thin the atmosphere, leading to colder, drier conditions. Evidence from various Mars missions suggests that this pattern of atmospheric thickening and thinning may have occurred multiple times throughout Martian history, creating cyclical climate changes. The timing of major eruptive phases at Olympus Mons, determined by counting impact craters on lava flows of different ages, appears to correlate with some of these proposed climate shifts. This suggests that the volcano's activity cycles may have directly influenced Mars's habitability over time. The water vapor released during eruptions would have been particularly significant for Mars's climate system. Under the warmer conditions created by volcanic greenhouse gases, this water could have participated in a temporary hydrological cycle, condensing as snow or rain, flowing as liquid water on the surface, and potentially collecting in lakes or small seas before eventually being lost through evaporation, freezing into subsurface ice, or breaking down through a process called photodissociation, where ultraviolet radiation splits water molecules into hydrogen and oxygen. The hydrogen, being extremely light, would easily escape to space, while some of the oxygen would combine with rocks on the Martian surface in oxidation reactions, contributing to the planet's distinctive red coloration. This process of water breakdown and hydrogen escape represents an irreversible loss mechanism that gradually dehydrated Mars regardless of volcanic inputs. However, during periods of intense volcanic activity at Olympus Mons and elsewhere, the rate of water vapor addition could have temporarily exceeded the loss rate, creating periods with active hydrological systems. Sulfur compounds from Olympus Mons eruptions would have created additional climate effects. Volcanic sulfur dioxide can form reflective aerosols in the upper atmosphere that block incoming sunlight, potentially cooling the planet. On Earth, large eruptions like the 1991 Mount Pinatubo event can cause measurable global cooling for several years. On Mars, major eruptive phases at Olympus Mons might have triggered similar cooling episodes, creating complex patterns of climate change as the warming effect of added greenhouse gases competed with the cooling effect of sulfur aerosols. The gradual evolution of Olympus Mons' eruptive style likely influenced its atmospheric contributions over time. Early eruptions from the developing volcano were probably more explosive, driven by higher gas content in the magma and possibly by interaction with subsurface water or ice. These explosive eruptions would have injected ash and gas high into the atmosphere, where they could spread globally and have maximum climate impact. Later eruptions, as indicated by the shield volcano structure, became more effusive, characterized by flowing lava rather than explosive ash, which would release gases more gradually and potentially have different atmospheric effects. As Mars cooled over billions of years, volcanic activity gradually declined in frequency and intensity. The most recent lava flows on Olympus Mons might be as young as 10 to 30 million years, geologically recent but not active on human timescales. This volcanic decline coincided with the continued loss of atmospheric gases to space, leading to the thin atmosphere we observe today. Current atmospheric pressure on Mars averages less than 1% of Earth's sea level pressure, insufficient for liquid water to exist stably on the surface except under very limited circumstances. The legacy of Olympus Mons' atmospheric contributions can still be detected today. The current Martian atmosphere is composed of about 95% carbon dioxide, consistent with a primarily volcanic source. Trace gases in the atmosphere, including sulfur compounds and certain isotopic signatures, provide additional evidence of the volcano's past influence. By studying these atmospheric components and comparing them with gases trapped in Martian meteorites of different ages, scientists can reconstruct aspects of the atmosphere's evolution over time and better understand Olympus Mons' role in that process. The relationship between Olympus Mons and Mars' atmosphere offers important insights for understanding climate evolution on other planets, including Earth. It demonstrates how volcanic activity can temporarily counter atmospheric loss processes on a planet without protective mechanisms like Earth's strong magnetic field and active carbon cycle. It also illustrates how a planet's volcanic history can create periods of potentially habitable conditions, even as the overall planetary evolution trends toward increasingly hostile surface environments. The atmospheric influence of Olympus Mons throughout Martian history has been gradually revealed through increasingly sophisticated observation techniques. Our understanding of this massive volcano has evolved dramatically as imaging and mapping technologies have advanced, with each generation of Mars missions providing more detailed and comprehensive data. These technological improvements have transformed Olympus Mons from a fuzzy bright spot in early telescopes to one of the most thoroughly documented geological features beyond Earth. The earliest attempts to map Olympus Mons relied on Earth-based telescopes, which could barely resolve the feature as a bright spot on the Martian surface. Astronomers in the late 19th and early 20th centuries could only record its general location and apparent brightness changes, often mistaking atmospheric clouds above the volcano for surface features. These limitations meant that until spacecraft visited Mars, even basic facts about Olympus Mons remained unknown or misunderstood. The first major breakthrough came with NASA's Mariner 9 mission, which entered Mars orbit in 1971. When the spacecraft arrived, Mars was experiencing a global dust storm, but as the dust settled, Mariner 9's cameras revealed the summits of several massive volcanoes poking above the dust clouds. These images provided the first hint of Olympus Mons' extraordinary scale. As the dust continued to clear, Mariner 9 captured complete images of the volcano, revealing its shield-like form, the complex caldera at its summit, and the escarpment around its base. Though revolutionary, Mariner 9's cameras were modest by today's standards, with a best resolution of about 100 meters per pixel. This meant smaller features remained undetectable, and precise measurements of the volcano's height and slope were approximate at best. Nevertheless, these first orbital images fundamentally changed our understanding of Olympus Mons, confirming its volcanic nature and establishing it as the largest volcano in the solar system. The Viking orbiters, arriving at Mars in 1976, carried improved camera systems capable of imaging at resolutions of up to about 30 meters per pixel. This higher resolution allowed scientists to identify individual lava flows, distinguish different portions of the caldera complex, and examine the structure of the basal escarpment in greater detail. Viking images revealed the texture of the volcano's surface, showing the characteristic ridged pattern of overlapping lava flows that built up the mountain over billions of years. While the Viking cameras provided better visual imaging, they could not directly measure elevation. The volcano's height had to be calculated indirectly using shadow measurements and stereoscopic image pairs. These methods produced reasonable estimates but had significant margins of error. Scientists knew Olympus Mons was extraordinarily tall, but its precise height remained uncertain. A quantum leap in Olympus Mons mapping came with NASA's Mars Global Surveyor mission, which reached Mars in 1997. This spacecraft carried the Mars Orbiter Laser Altimeter (MOLA), an instrument that fired laser pulses at the surface and measured the time taken for reflections to return, allowing precise elevation measurements. MOLA provided the first accurate topographic map of Olympus Mons, revealing its true height of approximately 25 kilometers above the surrounding plains and allowing scientists to measure its slopes with unprecedented precision. The MOLA data transformed our understanding of Olympus Mons by providing a three-dimensional perspective that previous imaging could not. Scientists could now quantify the volcano's volume, measure the depth of its caldera, and analyze the gradient of its slopes at different locations. The data revealed that despite its enormous height, Olympus Mons has remarkably gentle slopes averaging only about 5 degrees, confirming its classification as a shield volcano formed from highly fluid lava flows. Subsequent missions added new dimensions to our observations of Olympus Mons. The European Space Agency's Mars Express, arriving in 2003, carried the high-resolution stereo camera HRSC, which captured stunning colour images of the volcano and created detailed 3D models of its structure. These stereo images allowed scientists to create perspective views that showed Olympus Mons as it would appear to human eyes from different vantage points, helping both researchers and the public better visualize this enormous feature. NASA's Mars Reconnaissance Orbiter, reaching Mars in 2006, carried several instruments that revolutionized Olympus Mons imaging. Its context camera provided medium-resolution images covering large areas, while the high-resolution imaging science experiment, HiRISE, captured details as small as 30 centimeters across. These incredibly detailed images revealed individual boulders, small impact craters, and fine-scale textures of lava flows that had never been visible before. The level of detail was equivalent to being able to spot a dinner table on the volcano's surface from orbit. Beyond visible light imaging, Mars Reconnaissance Orbiter also carried spectroscopic instruments that could identify mineral compositions by analyzing how rocks absorb and reflect different wavelengths of light. The Compact Reconnaissance Imaging Spectrometer for Mars, CRISM, mapped variations in rock composition across Olympus Mons, helping scientists identify different types of volcanic materials and weathering products. These compositional maps revealed how the chemistry of eruptions changed over time and identified minerals formed through interaction with water or other volatiles. Another revolutionary development came from ground-penetrating radar instruments on Mars Express and Mars Reconnaissance Orbiter. The Mars Express MARSIS, Mars Advanced Radar for Subsurface and Ionosphere Sounding, and Mars Reconnaissance Orbiter's SHARAD shallow radar sent radar signals that penetrated below the surface and reflected from subsurface layers. While these instruments were primarily designed to detect subsurface ice, they also provided information about the internal structure of large features like Olympus Mons, revealing layers of lava flows and other structures hidden below the visible surface. Thermal imaging added another perspective through instruments like the Thermal Emission Imaging System, THEMIS, on NASA's Mars Odyssey orbiter, by measuring infrared radiation emitted by the surface. THEMIS created maps showing how different areas heat up during the day and cool at night. These thermal properties revealed variations in rock density, dust coverage, and other physical properties across Olympus Mons. Some areas retain heat longer than others, indicating differences in material composition or structure that aren't always visible in conventional images. The combination of these diverse imaging and mapping techniques has created a multidimensional view of Olympus Mons far beyond what any single instrument could provide. Scientists can now study the volcano's visible appearance, three-dimensional structure, internal composition, mineral makeup, thermal properties, and subsurface features, all from spacecraft orbiting hundreds of kilometers above. This comprehensive dataset allows researchers to reconstruct the volcano's formation history and evolution with unprecedented detail. Modern digital tools have further enhanced our ability to study Olympus Mons by combining data from multiple instruments into integrated models. Geographic Information Systems, GIS, allow scientists to overlay different types of data, visible images, elevation models, compositional maps, and more, creating comprehensive analytical tools. Virtual reality technologies have also been employed to create immersive experiences of Olympus Mons, allowing researchers to virtually walk the volcano's slopes and examine features of interest from any angle. Despite these advances, imaging and mapping Olympus Mons still faces challenges. The volcano's enormous size means that even high-resolution cameras can only capture small portions in detail at any one time. Frequent dust storms on Mars occasionally obscure surface features, interrupting observation campaigns. And without surface missions specifically targeting Olympus Mons, certain questions remain difficult to answer through remote sensing alone, such as the precise age of specific lava flows or the detailed mineralogical composition of rocks that might be altered or weathered in ways not easily detectable from orbit. Future mapping efforts will likely include even higher resolution cameras, more sensitive spectrometers, and advanced radar systems that can penetrate deeper into the volcano's structure. Perhaps most exciting is the prospect of eventual aerial mapping using drones or aircraft specifically designed for Mars's thin atmosphere, which could provide a middle ground between orbital and surface observations. Such platforms could fly above the slopes of Olympus Mons, capturing close-range images and data not possible from orbit while covering far more territory than a land-based mission. The increasingly detailed mapping of Olympus Mons has led scientists to a fascinating question. Could this enormous volcano still be active in some way, while traditionally classified as dormant or extinct? Recent observations have prompted researchers to reconsider whether Olympus Mons might have experienced volcanic activity in the geologically recent past, or whether it might even retain some level of activity today. The question of recent activity at Olympus Mons begins with determining the age of its youngest lava flows. Scientists primarily use crater counting for this purpose, a technique based on the principle that older surfaces accumulate more impact craters over time. By counting the number and size of craters on different lava flows, researchers can estimate how long those surfaces have been exposed to bombardment from space. These crater counting studies have yielded surprising results. Some of the youngest-looking lava flows on Olympus Mons appear to be remarkably recent in geological terms, perhaps just tens of millions of years old, with some studies suggesting ages as young as 2 million years for certain areas. While this might sound ancient by human standards, in geological terms it's quite recent, especially considering Mars's overall geological activity has generally been thought to have declined dramatically billions of years ago. The possibility of such recent activity raises intriguing questions about Mars' interior heat. For a planet to generate magma, its interior must be hot enough to melt rock, typically requiring temperatures above 1000 degrees Celsius. Conventional models of Mars' thermal evolution suggested the planet should have cooled substantially over its 4.5 billion year history, with most volcanic activity ending billions of years ago. The evidence for much more recent lava flows challenges these models, suggesting that at least certain regions of the Martian interior have remained hot enough for magma generation much longer than expected. Several factors might explain this extended volcanic lifetime. Olympus Mons sits atop the Tharsis Bulge, a region with anomalously thick crust that might contain higher concentrations of radioactive elements like uranium, thorium, and potassium. The decay of these elements produces heat, potentially maintaining higher temperatures in this region. Additionally, the sheer size of Olympus Mons might create insulating effects, trapping heat beneath the massive pile of volcanic material and allowing magmatic systems to remain active longer than in other areas. Beyond crater counting, other lines of evidence suggest possible recent or even current activity. Orbital spectrometers have detected localized emissions of methane in the Martian atmosphere, a gas that on Earth often associates with either biological activity or volcanic or geothermal processes. While these methane detections remain controversial and their source uncertain, some scientists have proposed that low-level volcanic or hydrothermal activity, possibly associated with the Tharsis volcanic province, including Olympus Mons, could be responsible. Thermal imaging has identified what might be subtle temperature anomalies in certain areas of Olympus Mons and the broader Tharsis region. While these temperature differences are small, typically just a few degrees, they might indicate areas where residual heat from cooling magma bodies is still reaching the surface. Alternative explanations exist, including differences in surface material properties or measurement artifacts. But the possibility of genuine thermal anomalies remains intriguing. Geophysical models of Mars' interior suggest that while large-scale, surface-reaching eruptions might have ceased, smaller magma bodies could potentially still exist at depth. These might not produce dramatic surface eruptions but could drive hydrothermal systems where groundwater or ice interacts with hot rocks, creating chemical reactions and potentially releasing gases. Such subsurface activity would be difficult to detect from orbit, but could represent a form of ongoing volcanic activity. The question of current or recent activity at Olympus Mons has implications beyond pure geological interest. Active or recently active volcanic regions would be prime targets for astrobiological investigation. On Earth, hydrothermal systems associated with volcanism often support thriving microbial ecosystems, even in otherwise hostile environments. If similar systems exist or existed recently on Mars, they could potentially provide habitats for simple Martian life forms, if such life ever evolved. For future human exploration, the possibility of recent or residual activity creates both opportunities and concerns. Geothermally active regions might provide valuable energy resources for a Martian outpost, offering access to heat that could generate power or support life support systems. However, any current activity, even at low levels, would also present potential hazards that mission planners would need to consider. Definitively answering questions about Olympus Mons' current activity level will likely require new types of observations. Surface seismometers, like the one deployed by NASA's InSight mission, though located far from Olympus Mons, can detect marsquakes that might be associated with magma movement. More such instruments, particularly placed nearer to Olympus Mons, could help detect any current internal activity. Gas monitoring instruments with higher sensitivity than current orbiters could better detect volcanic emissions if they exist. Perhaps most conclusively, direct sampling and dating of the youngest lava flows would provide much more precise age determinations than crater counting alone. This would require surface missions specifically targeting these young-looking areas of Olympus Mons, a challenging prospect given the difficult terrain and the need to navigate the volcano's enormous slopes, but potentially achievable with advanced rovers or sample return missions in the coming decades. While the debate about Olympus Mons' current activity status continues, the evidence increasingly suggests that this enormous volcano had a much longer active lifetime than once thought, extending well into Mars' recent geological past. Whether some level of activity continues today remains an open question, one of many mysteries still surrounding this extraordinary feature that continues to fascinate scientists and space enthusiasts alike. The question of whether Olympus Mons might still harbour some level of activity leads naturally to one of its most distinctive features, its summit caldera complex. This enormous depression at the top of the volcano offers perhaps our best window into Mars's interior, revealing crucial information about the magmatic processes that built this giant and the internal structure of the planet itself. The caldera complex at Olympus Mons' summit is truly massive, spanning approximately 80 kilometers across, large enough to contain an entire major city. Unlike the simple crater found atop many volcanoes, Olympus Mons features a compound caldera consisting of at least 6 overlapping circular depressions. Each of these individual calderas ranges from 15 to 60 kilometers in diameter and reaches depths of up to 3 kilometers below the surrounding rim. The nested, overlapping arrangement tells a story of repeated cycles of activity over the volcano's long history. These calderas formed through a process fundamentally different from impact craters. Each formed when magma withdrawing from beneath the summit caused the unsupported surface to collapse downward into the partially emptied magma chamber below. This typically happens during or after a major eruption, when significant volumes of magma are expelled from the subsurface reservoir. The timing and location of each collapse event provide critical information about how the magma system beneath Olympus Mons evolved over time. By examining the sequence of overlapping relationships between the different calderas, scientists have reconstructed a rough chronology of these major collapse events. The oldest identifiable calderas appear in the northwestern portion of the complex, while the youngest are found in the southeast, suggesting a gradual migration of the main magma chamber in that direction over time. This migration might reflect changes in the underlying plumbing system as the volcano continued to grow and evolve. The walls of these calderas expose layered materials that would otherwise remain hidden beneath the surface, creating a natural cross-section through the upper portions of the volcano. High-resolution orbital images reveal distinct layers of varying thickness, color, dot, and texture, each representing a different lava flow or volcanic deposit. Some layers appear dark and massive, suggesting dense, fluid lava flows, while others show a lighter, more rubbly texture indicative of more explosive activity or flows that fragmented as they cooled. Spectroscopic instruments in orbit have analysed the mineral composition of these exposed layers, identifying mainly basaltic materials but with subtle variations that record changes in magma chemistry over time. Earlier flows appear to contain slightly different mineral assemblages than later ones, suggesting the magma source region evolved as the volcano continued to draw material from Mars's mantle. These compositional variations provide critical clues about the planet's internal differentiation, how materials of different densities and compositions separated as Mars cooled from its initial formation. The depth of the calderas allows scientists to estimate the approximate location of the magma chambers that once existed beneath the summit. Based on the mechanics of caldera formation and the observed dimensions of the collapse features, these chambers likely resided at depths of about 10 to 20 kilometers beneath the summit. This places them within Mars' crust rather than directly connecting to the deeper mantle, suggesting a complex plumbing system where magma was stored and evolved before erupting. Detailed imaging of the caldera floors reveals fascinating post-collapse features. Numerous fractures and small faults crisscross the relatively flat floors, creating patterns that record how the collapsed material adjusted and settled. Some areas show evidence of more recent small-scale volcanic activity, localized vents, minor cones, and lava pools that formed after the main caldera-forming events. These features indicate that even after major collapses, volcanic activity often continued, albeit at a reduced scale. One particularly interesting aspect of the Olympus Mons calderas is evidence for subsidence beyond the main collapse events. Subtle concentric fractures surrounding the caldera complex suggest broader sagging of the summit region, potentially indicating more gradual withdrawal of magmatic support. This pattern differs from the sharp, cliff-like boundaries of the main calderas and points to complex, multi-stage adjustments of the volcano's summit as its internal support system evolved. Some portions of the caldera walls show signs of mass wasting, where material has slumped or fallen from the steep cliffs created by collapse. These landslides expose even fresher material and create debris aprons on the caldera floors. The scale of some of these landslides is impressive, with individual events involving millions of cubic meters of material. Studying these mass-wasting features helps scientists understand not just the composition of the volcano, but also how its materials behave mechanically under Martian conditions. The floor of the caldera complex isn't uniformly flat, but contains subtle elevation differences that tell yet another story about its formation history. Some sections appear to have dropped lower than others, creating distinct benches at different levels. These elevation differences likely reflect variations in the depth or extent of magma withdrawal beneath different portions of the summit, or possibly separate collapse events that weren't dramatic enough to create distinct, recognizable calderas. Perhaps most intriguing are features that might indicate volatile activity within the caldera complex. Some areas show textures and coloration consistent with potential hydrothermal alteration, where hot magmatic fluids interacted with rocks, potentially changing their mineral composition. If confirmed, these alterations would provide evidence not just of heat, but of water or other volatiles participating in the volcanic system, a finding with significant implications for Mars' water budget and potential for past habitable environments. The timing of caldera formation events provides crucial information about the volcano's most active periods. By counting impact craters on different caldera floors, scientists estimate that the visible caldera complex formed over a period spanning hundreds of millions to perhaps a billion years, with the youngest sections possibly as recent as a few 100 million years old. This extended time frame reinforces the picture of Olympus Mons as a volcano that remained active far longer than typical volcanoes on Earth. Comparing the Olympus Mons caldera with similar features on Earth's volcanoes highlights both similarities and differences. The basic collapse process appears similar to what forms calderas on large shield volcanoes like Mauna Loa in Hawaii. But the Martian example developed over a much longer timescale and reached far larger dimensions. This comparison helps calibrate models of how volcanic processes operate under different planetary conditions. For future exploration, the caldera complex represents one of the most scientifically valuable targets on Olympus Mons. A mission to the caldera floor would provide access to materials from various depths and time periods in the volcano's history, all in a relatively small geographical area. Samples from the caldera walls could provide a stratigraphic record spanning potentially billions of years of Martian geological evolution, making it a natural drilling site without actually requiring deep drilling. The caldera of Olympus Mons thus serves as both a record of the volcano's eruptive history and a window into the broader story of Mars as a planet. By reading the layers exposed in its walls, analysing the patterns of collapse, and studying the composition of its materials, scientists continue to refine our understanding of not just this extraordinary volcano, but of the internal workings of our neighbouring planet throughout its long history. While Olympus Mons stands as the largest volcano in our solar system, it exists within a broader context of volcanic giants found across different worlds. Comparing these massive structures reveals fascinating patterns about how planetary conditions shape volcanic activity and provides important perspective on what makes Olympus Mons both typical and exceptional among its volcanic cousins. Mars itself hosts several other enormous volcanoes that rival Olympus Mons in scale. The three aligned peaks of the Tharsis Montes, Ascraeus Mons, Pavonis Mons, and Arsia Mons, each rise between 15 and 18 kilometres above the surrounding plains and span hundreds of kilometres at their bases. While smaller than Olympus Mons, they would still dwarf any volcano on Earth. These three volcanoes share many characteristics with their larger sibling. including shield-like structures built from fluid lava flows, complex summit calderas, and evidence of long-lived activity. Olympus Mons, formerly called Alba Patera, located north of Olympus Mons in the Tharsis region, represents a different style of Martian volcanism. While rising only about 6 kilometers above the surrounding terrain, modest by Martian standards, Olympus Mons spreads over an extraordinary area, with a base diameter exceeding 1,000 kilometers. This makes it potentially the most aerially extensive volcano in the solar system, covering more surface area than even Olympus Mons despite its lower profile. It's unusually broad. Low shape suggests its lava had even lower viscosity or erupted at higher rates than the lava that built other Martian volcanoes. The ancient highland regions of Mars contain additional volcanic features from the planet's earliest history. The Syrtis Major region includes a broad volcanic plain dating back more than 3 billion years, while the Elysium region hosts another cluster of significant volcanoes including Elysium Mons, Hecate's Tholus, and Albor Tholus. These older volcanic provinces typically show more signs of erosion and modification than the Tharsis volcanoes, providing a contrast that helps scientists understand how Martian volcanism changed over the planet's history. Beyond Mars, Venus offers the closest comparison to Olympus Mons in terms of volcanic style and scale. Venus hosts numerous large shield volcanoes, with Mart Mons among the largest, rising about 8 kilometers above the surrounding plains and spanning several hundred kilometers at its base. While impressive, even Venus's largest volcanoes don't match Olympus Mons in height, a difference attributed primarily to Venus's stronger gravity, which is similar to Earth's and limits how high mountains can grow before deforming under their own weight. What Venus lacks in volcanic height, it makes up for in variety and number. Radar mapping by the Magellan spacecraft revealed more than 1,000 volcanic features across the Venusian surface, including shield volcanoes, vast lava plains, unusual pancake domes formed by highly viscous lava, and spider-like networks of fractures and small volcanoes called arachnoids. This diversity suggests that Venus has experienced more varied volcanic processes than Mars, possibly due to greater variations in lava composition and eruption conditions. One striking difference between Venusian and Martian volcanism is the apparent lack of plate tectonics on both worlds, yet with different outcomes. Like Mars, Venus has a stagnant single-plate surface, but instead of developing a few enormous volcanoes like Olympus Mons, Venus shows more distributed volcanic activity across its surface. This different pattern might result from Venus's higher internal temperatures, thinner lithosphere, or periodic global resurfacing events, factors that continue to puzzle planetary scientists. Jupiter's moon Io represents the most volcanically active body in our solar system, with more than 400 active volcanoes observed during just a few decades of spacecraft observations. Unlike the shield volcanoes that dominate Mars and Venus, Io's volcanism creates different structures, numerous caldera-like depressions, vast plains covered with fresh sulfur-rich deposits, and mountains that appear to have formed through tectonic forces rather than direct volcanic construction. The extraordinary volcanic activity on Io is driven by a fundamentally different mechanism than that of rocky planets. Gravitational interactions with Jupiter and neighbouring moons create powerful tidal forces that flex Io's interior, generating enough heat through friction to maintain widespread, vigorous volcanism. This tidal heating produces eruptions far more energetic than those that built Olympus Mons, with plumes of sulfur and sulfur dioxide shooting hundreds of kilometers above Io's surface. The Earth, despite its smaller size compared to Mars and Venus, hosts several massive shield volcanoes that provide our best analogue for understanding Olympus Mons. The Hawaiian Islands represent the largest volcanic structures on Earth, with Mauna Loa rising approximately 9 kilometers from its base on the Pacific Ocean floor to its summit, though only about 4 kilometers stands above sea level. If measured by total volume, Mauna Loa contains approximately 10,000 cubic kilometres of material, impressive by Earth standards, but still less than 1% the volume of Olympus Mons. Several factors explain why Earth's volcanoes remain modest compared to their Martian counterparts. Earth's active plate tectonics means that the crust continuously moves over hotspots, creating chains of volcanoes rather than allowing a single volcano to grow for billions of years. Higher gravity limits the height mountains can achieve before slumping under their own weight. More substantial erosion from water, ice, and weather constantly works to wear down volcanic structures, and Earth's thinner lithosphere cannot support the weight of extremely large volcanic structures without bending or breaking. The island of Iceland represents another interesting Earth comparison, formed where a volcanic hotspot coincides with the mid-Atlantic ridge spreading centre. This combination creates extensive volcanic activity, building the entire island through repeated eruptions. While no single Icelandic volcano approaches Olympus Mons in scale, the island demonstrates how prolonged volcanism can construct substantial landmasses over geological time. Beyond the terrestrial planets, the outer solar system hosts a different type of volcanism on icy moons, cryovolcanism, where water, ammonia, or methane replaces molten rock as the erupting material. Neptune's moon Triton, Saturn's moons Enceladus and Titan, and possibly Jupiter's Europa and Ganymede all show evidence of this cold volcanic process. While operating at much lower temperatures than rocky volcanism, these systems can still create impressive structures, with Right Mons on Pluto potentially representing one of the largest cryovolcanic features at about 150 kilometres across and 4 kilometres high. These diverse volcanic expressions across the solar system highlight how fundamental planetary characteristics, size, dot, composition, heat sources, crustal structure, and gravity influence volcanic processes and the structures they create. Olympus Mons represents an end-member example of what volcanism can achieve under specific conditions. A planet large enough to maintain internal heat for billions of years, but small enough that gravity doesn't prevent extreme vertical growth. A static crust allowing prolonged activity at a single location. Minimal erosion preserving structures once formed. And fluid basaltic lava capable of travelling great distances to build a broad shield structure. The study of these comparative examples enhances our understanding not just of Olympus Mons itself, but of volcanic processes as a fundamental force shaping worlds throughout our solar system. Each volcanic giant, whether on Mars, Venus, Earth, Dot, or beyond, represents a unique experiment in planetary volcanism, a different combination of conditions producing different but related outcomes. By studying these variations, scientists continue to refine models of how planets evolve, how their interiors and surfaces interact, and how the diverse landscapes we observe came to be. This comparative perspective also informs our search for volcanism on exoplanets orbiting other stars. As we develop the ability to detect surface features on distant worlds, understanding the full range of volcanic expressions in our own solar system provides crucial context for interpreting these observations. The lessons learned from Olympus Mons and its volcanic cousins will help scientists recognize and interpret volcanic features across the galaxy, expanding our understanding of geological processes beyond our solar neighborhood. The comparative study of volcanic features throughout our solar system provides crucial context for future exploration efforts, particularly as space agencies and private companies develop increasingly ambitious plans for Mars missions. As these plans evolve, Olympus Mons occupies a unique position, simultaneously representing one of the most scientifically valuable targets on Mars, while also presenting extraordinary logistical challenges that will require innovative solutions and technologies. Current Mars exploration has largely focused on regions with evidence of past water activity, primarily seeking insights into the planet's potential habitability and searching for signs of ancient microbial life. These priorities have directed most missions to relatively flat lowland areas, ancient river valleys, and lake beds, environments quite different from the massive volcanic terrains of Tharsis. However, as Mars exploration matures and diversifies, Olympus Mons and its surrounding volcanic province are likely to become increasingly important destinations. Several space agencies have begun incorporating Olympus Mons into their long-term Mars exploration roadmaps. NASA's Mars Exploration Program Analysis Group has identified volcanic processes as one of several high-priority science themes for future missions. The European Space Agency's Mars Robotic Exploration Preparation Program has similarly highlighted volcanic regions as important for understanding Mars' thermal and geological evolution. While immediate missions remain focused elsewhere, these planning documents suggest Olympus Mons will feature more prominently in later exploration phases. The volcanic terrain surrounding Olympus Mons may serve as a stepping stone before tackling the mountain itself. The vast lava plains at the volcano's base offer relatively smooth, flat surfaces potentially suitable for landing spacecraft. These areas provide access to volcanic materials that flowed from Olympus Mons while avoiding the challenging topography of the mountain itself. A mission to these peripheral regions could analyze relatively recent lava flows, potentially dating them with greater precision than currently possible through crater counting methods alone. When missions eventually target Olympus Mons directly, they'll likely begin with robotic exploration. Specialized rovers designed for long-distance travel and capable of navigating gentle but extended slopes would be necessary to traverse significant portions of the volcano. Given the enormous scale of Olympus Mons, such rovers would need substantially greater range than current vehicles like Perseverance, which typically covers just a few hundred meters per day. Advanced autonomous navigation systems would be essential, allowing rovers to travel longer distances between communications with Earth. Certain areas of Olympus Mons hold particular scientific appeal for future missions. The basal escarpment, with its exposed cross-section of the volcano's structure, offers access to multiple layers of its construction history within a relatively small area. The summit caldera complex provides a window into the volcano's most recent activity phases and potentially its deepest materials. The boundary between different aged lava flows could reveal crucial information about how Mars's volcanic activity evolved over time. Sample return from Olympus Mons represents a particularly high-value objective. While current Mars sample return efforts focus on sedimentary materials relevant to the search for past life, volcanic samples from Olympus Mons would address different but equally fundamental questions about Mars' interior composition, thermal history, and mantle evolution. Obtaining properly dated samples from different elevations of the volcano would allow scientists to reconstruct its eruption timeline with unprecedented precision. The challenge of exploring such an enormous feature has prompted innovative mission concepts. One approach involves deploying multiple smaller rovers or drone-like aerial vehicles that could work cooperatively to survey different areas simultaneously. Another concept proposes establishing a primary base station at a strategic location with multiple smaller scout vehicles operating in a hub-and-spoke model to extend the exploration range. Aerial platforms may prove particularly valuable for Olympus Mons exploration. Mars helicopter technology, first demonstrated with NASA's Ingenuity helicopter in 2021, could evolve into more capable aircraft specifically designed for volcanic terrain reconnaissance. Such platforms could cover far greater distances than ground vehicles and access areas too steep or rugged for rovers. The thin atmosphere at higher elevations would present challenges for aircraft operation, but specially designed vehicles might navigate at least the lower and middle portions of the mountain. Beyond robotic missions, Olympus Mons features prominently in long-term human exploration scenarios. While immediate plans for human Mars missions focus on more accessible equatorial regions, longer-term visions often include expeditions to Olympus Mons as exploration capabilities mature. The volcano's scientific value, distinctive environment, and symbolic importance make it a compelling destination once the initial human outposts have been established. A human expedition to Olympus Mons would require substantial infrastructure development, given the distances involved. A dedicated surface transportation system, perhaps pressurized rovers capable of multi-week excursions, would be necessary. Alternatively, a series of smaller outposts might be established at different elevations, allowing staged exploration of the mountain's various regions. The lower gravity of Mars would somewhat ease the physical burden of climbing, but the sheer scale of Olympus Mons would still make its exploration a massive undertaking. The diverse environments at different elevations on Olympus Mons could support a variety of research activities. Lower elevations, with relatively higher atmospheric pressure, might host primary habitats and agricultural modules. Mid-elevation research stations could study the volcano's structure and composition through drilling or sampling exposed layers. The summit region, with its thin atmosphere and unobstructed views, could support astronomical observatories taking advantage of the stable atmospheric conditions and reduced light pollution. Resource utilization will play a crucial role in extended missions to Olympus Mons. The volcano's abundant basaltic material could provide raw materials for construction, while subsurface ice deposits might offer accessible water. Lava tubes, if present and stable, might serve as natural shelters requiring minimal modification to protect against radiation and temperature extremes. The potential for geothermal heat at certain locations could provide energy for long-duration missions. Several technical challenges must be overcome before extensive exploration of Olympus Mons becomes feasible. Power generation represents a significant hurdle, as solar efficiency decreases during dust storms and at higher latitudes. Advanced nuclear power systems or new solar technologies might address this challenge. Communications infrastructure would need enhancement, with relay satellites positioned to maintain contact with explorers across the volcano's vast expanse. Life support systems capable of functioning reliably across the extreme environmental gradient from base to summit would require careful engineering. Despite these challenges, Olympus Mons represents an exploration prize worth pursuing. Its unique combination of scientific value, resource potential, and inspirational appeal ensures it will feature prominently in our long-term future on Mars. The volcano offers a natural laboratory for understanding fundamental planetary processes, a potential home for specialized research facilities, and a proving ground for technologies that might eventually be applied to other worlds. As our presence on Mars gradually expands from initial footholds to broader exploration, Olympus Mons awaits as both a formidable challenge and an extraordinary destination. The role that Olympus Mons will play in future Mars exploration connects directly to its broader cultural significance, beyond its scientific importance. This enormous volcano has captured human imagination and influenced how we perceive the red planet. From its first detection as a mysterious bright spot by early astronomers to its current status as an iconic Martian landmark, Olympus Mons has shaped our cultural understanding of Mars in profound and lasting ways. The cultural impact of Olympus Mons began before anyone even knew it was a volcano. When early astronomers glimpsed the bright spot they named Nix Olympica, or Snows of Olympus, they were connecting Mars to Earth's mythology, specifically to Mount Olympus, the legendary home of the Greek gods. This classical reference established an early link between Martian features and human cultural touchstones, a practice that continues in the naming of many Martian landmarks today. When Mariner 9 revealed Olympus Mons as a volcano of unprecedented size in 1971, it fundamentally altered public perception of Mars. Previous imaginings of Mars, influenced by Percival Lowell's mistaken observations of canals, had pictured a planet crisscrossed by engineered waterways built by a dying civilization. The discovery of Olympus Mons shifted this narrative dramatically, presenting Mars as a world of extraordinary natural features rather than artificial constructions. This massive volcano became evidence that Mars, while different from Earth, followed similar geological principles, just with more extreme results. Throughout the 1970s and 80s, as more detailed images became available, Olympus Mons quickly established itself as the defining geographical feature of Mars in popular culture. Documentaries, science textbooks, museum exhibits, and space advocacy materials frequently featured this superlative mountain. Its extreme scale made it an effective ambassador for Mars in educational contexts. Teachers could capture student interest by comparing this extraordinary feature to familiar Earth mountains, making Mars seem both alien and relatable simultaneously. Science fiction writers particularly embraced Olympus Mons as a dramatic setting. Arthur C. Cole Clarke mentioned it in his novel The Sands of Mars, even before its true nature was known, while later authors like Kim Stanley Robinson made extensive use of the volcano in his acclaimed Mars trilogy. In Robinson's books, Olympus Mons serves as both a formidable climbing challenge for early Martian settlers and later becomes the site of major settlements utilizing the mountain's varied elevations and environments. These fictional treatments helped cement the volcano's place in cultural imagination as not just a scientific curiosity, but a potential future home for humanity. Visual artists have been similarly inspired by Olympus Mons, creating countless representations of the massive volcano across various media. These range from scientifically accurate digital renderings used by space agencies to more imaginative interpretations in paintings, digital art, and sculpture. The distinctive shield shape with its central caldera complex has become one of the most recognizable extraterrestrial landscapes, instantly identifiable even to those with only casual interest in astronomy or planetary science. This visual distinctiveness has made Olympus Mons a staple in entertainment media beyond literature. Films like The Last Days on Mars and Red Planet feature the volcano as a backdrop or plot element. Video games set on Mars, including entries in popular series like Doom, Mass Effect, and Call of Duty, frequently include Olympus Mons as a landmark or level setting. The volcano's dramatic scale provides game designers with a natural justification for vertically oriented gameplay and spectacular vistas that emphasize the alien Martian environment. The cultural significance of Olympus Mons extends beyond entertainment into education and public engagement with planetary science. Museum exhibits about Mars typically feature models or imagery of the volcano, using its superlative size to draw visitor interest. Planetarium shows and astronomy apps highlight it as a must-see feature when exploring digital Mars. Public lectures about Mars by scientists and educators almost invariably include discussion of Olympus Mons, using it as an entry point to explain broader concepts about comparative planetology and geological processes. Social media has further amplified the cultural reach of Olympus Mons. Striking images of the volcano regularly generate significant engagement online, with users expressing wonder at its scale and asking questions about how such an enormous feature formed. These interactions help build public support for Mars exploration and science funding more broadly, demonstrating how a single impressive feature can serve as a gateway to deeper interest in planetary science. Beyond its role in entertainment and education, Olympus Mons has acquired symbolic significance in discussions about human potential and achievement. As the highest mountain in our solar system, it represents an ultimate climbing challenge, a future feat that would far surpass summiting Everest or any other terrestrial peak. Mountaineering organizations and adventure enthusiasts sometimes speak of Olympus Mons as the ultimate future objective, a dream summit that symbolizes the expansion of human exploration beyond Earth. For space settlement advocates, Olympus Mons often features prominently in long-term visions of a terraformed or settled Mars. Its enormous size and varied elevation zones are seen as potential assets for future colonization, offering different atmospheric pressures and conditions at different heights that could be advantageous during a gradual terraforming process. Conceptual artwork of future Martian cities often places settlements along the slopes of Olympus Mons, utilizing its natural features for both practical and aesthetic purposes. The volcano also appears frequently in discussions of human identity and perspective. The famous overview effect describes how seeing Earth from space fundamentally changes astronauts' perspective on our planet and humanity's place in the cosmos. Futurists and philosophers extend this concept to imagine how standing on Olympus Mons, seeing a curvature of another world while looking out from the highest point in the solar system, might similarly transform human consciousness and identity once we become a multiplanetary species. In educational contexts, Olympus Mons serves as a powerful tool for teaching scale and comparison. Teachers use the volcano to help students comprehend vast geological timescales, showing how its formation over billions of years contrasts with human history measured in mere thousands of years. The mountain also helps illustrate how different planetary conditions produce different outcomes from similar processes, demonstrating fundamental principles of planetary science in a concrete, visualizable way. Perhaps most significantly, Olympus Mons has become a symbol of Mars itself, an iconic feature that immediately evokes the red planet in popular imagination, similar to how the Grand Canyon symbolizes the American West or Mount Fuji represents Japan. When media outlets need a visual shorthand for Mars, images of Olympus Mons frequently appear alongside the more traditional full-disk views of the planet. This iconic status ensures that the volcano features prominently in public-facing communications about Mars exploration and science. The cultural impact of Olympus Mons continues to evolve as our relationship with Mars develops. Each new Mars mission provides improved data and imagery, allowing more accurate and detailed representations in both scientific and cultural contexts. As human missions to Mars move from concept to reality in coming decades, Olympus Mons will likely take on new significance, transforming from a distant object of wonder to a potential destination for human exploration and perhaps eventually a home for some of the first permanent Martian settlements. This cultural dimension of Olympus Mons complements its scientific importance, creating a feature that resonates across multiple aspects of human experience. As the largest mountain and volcano in our solar system, it captures something fundamental about both Mars as a planet and humanity's relationship with exploration and discovery. From ancient astronomers glimpsing a bright spot on a distant world to future explorers who might one day stand upon its slopes, Olympus Mons connects us to the broader story of how we understand our place in the cosmos and our potential future beyond Earth.